right, sound check. It doesn't look like I'm getting sound. Let's see, one more time, sound check. And it looks like I'm getting nothing. Why is that? Let me see if maybe a setting over here needs adjustment first. Okay, now can I hear myself? Also no. What is wrong? I know my microphone is working. Is it? Let me check. Audio input device. Yeah, it's the right device. Why is there no sound coming in? Let me see if I can open up the settings and figure out what's going on here. No, can't do that there. What about now? Can I hear myself now? Okay, that fixed it. Next thing to check. Oh, this is going to be, hold on. Okay, that's the screen set up the way I want it. Anyway, next thing to check is visuals. Is video working just fine? Yep, that looks good to me. All right, now we can finally take the headphones off and get started. That took what, 2 whole minutes, 2.5 minutes. But hey, better safe than sorry. I mean, 2 minutes is a small price to pay compared to having an entire 2, 3, potentially 4-hour stream ruined due to failing to do an audio check. This is why I do the checks. Can't wait to see what the stream recording looks like. Maybe it was just an audio issue on my end and everyone else was hearing things just fine. But now that we've got our technical hiccups out of the way, let's go ahead and talk about what we're doing today. So today, the goal is to wrap up this chapter on simple harmonic motion. And also there was something I forgot from rotational dynamics that I'm going to want to comment on. I've made a note for myself so that I don't forget it again. Here's hoping that I remember to look at my notes for that. And we're going to correct a derivation proof that we failed at last time, which was proving that you can just use the extension from the new equilibrium position for a vertical spring and end up treating it like a horizontal spring. I don't see where I attempted to do that here, but wherever I did it, oh, here it is. Yeah, this thing, we're going to fix this. And we're going to introduce some more equations today for simple harmonic motion, and we're just going to do a bunch of problems after that, and that'll be that. And then we'll be heading off to fluid mechanics next time. That is the goal. Here's hoping that nothing goes wrong, no technical issues, no power or internet outages or anything of that sort. Let's go ahead and get started. I'm actually not entirely sure where I want to start. So for homework, I had you guys do a worksheet which came with an answer key, so hopefully you guys were able to complete that. without any trouble. Hopefully the answer key helped there. But it basically had you practice calculating frequency and period just from, basic information like the amount of repetitions that occurred and the amount of time it took for those repetitions to occur. Hopefully you were able to figure out that number of repetitions divided by time equals frequency, and time divided by number of repetitions equals period, just based on their definitions. We also had, among those problems in the worksheet, a lot of problems where you had to just do like rearrangements, algebraic rearrangements of equations that looked like this to solve for one of the variables. So hopefully you did that as well. And I think there was also some practice in there, which was given some information about springs. Calculate their period. If you know the mass and spring constant, calculate the mass. If you know the period and spring constant, calculate the spring constant. If you know the period and the mass, and similar business just with frequency instead of period. So I guess 6 different types of questions you could be asked there. I don't remember if amplitude was a thing on that worksheet. I don't have it open in front of me right now. Maybe I should have opened it in preparation for this stream, but hopefully you got some practice in using these equations. We'll do some problems using them as well, but that'll be for later. Before that, I want to accomplish a couple of things. So first thing I want to do is fix that proof that I couldn't do properly last time. So let me go ahead and find where it was that I did it. Yeah, this over here. No, wait, this was the force version of the proof. Where was the other version of it that I attempted to do? Okay, here it is. This was where I was attempting to do this problem. So let me actually see. I was planning on just restarting the proof from scratch, but if there's anything in here that I can fix immediately, then that would be better. Oh, and that's a K that I missed last time. That should have been a K. Anyway, so that's good. Yeah, you know what? I'm just gonna start fresh. I don't want to try and navigate whatever I was doing last time with this attempt at a proof. I'll just start fresh. So let's prove energy-wise that a vertical spring is equivalent to a horizontal spring if you simply use the new equilibrium position of the vertical spring after a mass has been attached to it. So here's the spring at its default length. And then here's the spring having been stretched a bit after a mass has been attached to it. And that mass is gently let down until it's at rest with the spring, until the spring force exactly cancels out the weight of the object being attached to it. And then here I'm going to say that after it has reached this position, it gets set in motion, and we're looking at it at some point down here. So those are the 3 different states that we want to look at. So here is the spring at its default length. Here it is at a length of, we'll say that this distance is A. And then over here I called this distance b last time, I'm pretty sure. And then I said that this in-between distance was c. Or maybe it was the other way around. Maybe this was a and this was b and this was c, but we'll just use the names I've given them here, regardless of what it was that I tried last time. So let's go ahead and also write that at this point over here, when it's stretched a distance a, this is where the spring force, Ka, the magnitude of the spring force, spring constant times stretch distance, is equal to the weight. They must cancel out, so Ka equals mg. My mistake last time was that I tried to solve for a here and wrote a equals mg over k, and that led to a lot of confusion when writing the algebra because, you know, fractions being the messy things that they are made it easy for me to miss a step somewhere along the way. So I'm just going to keep it like this time. This time I'm just going to keep it like this. Okay, and the other big mistake I made was I think I compared the wrong 2 points. I think I compared between here and here when I should have just compared this point to this point. Using this point doesn't make any sense because this is before the mass is attached. I guess you could use this point when the mass is attached. That can work. You can get something out of that. But anyway, I'm going to compare these 2 points, and I'm going to say that up here, you are going to have kinetic energy of 1/2 mv1 squared. It's actually going to be v max, but let's call it v1 just for now. 1/2 mv1 squared plus an elastic potential energy of 1/2 k a squared, because this is a meters away from the original unstretched length of the spring, plus gravitational potential energy of mg what? Let's see. I guess it would be mgc if I set this to be my zero of potential energy. So this is going to be my h equals 0 position. So plus mgc. And that's going to equal over here. I could say that this is at rest, or I could say that it still has some speed and that it continues to go down after this point. If it's the lowest point, then the speed would be 0, but if it's not the lowest point, then the speed would be v2. So I'm just going to say it has kinetic energy 1/2 mv2 squared, and if v2 happens to be 0, then that'll be a special case that we can work with once we're done doing our algebra here. Plus 1/2 k, let's see. So it would be 1/2 kb squared at this point, if we're just calculating from, again, the rest length of the spring down to here. That's a distance of b, is what I called it, plus 0. I've set the potential energy to be 0 here. If v2 is not 0, then that just means that the lowest point is actually below h equals 0, and I guess I could have drawn another line down here and set that to be h equals 0 and then given this another name like h equals d, but it's fine. It's not going to make that much of a difference. I guess actually the difference it would make if I did that is it would make the algebra more complicated than it needs to be. This is the lowest point that we have, even if it's not the lowest point that this spring can reach. So I'm still gonna set this to 0 anyway. And yeah, let's go ahead and do some algebra. So I probably didn't even leave myself enough space here, but we'll see. So 1/2 mv1 squared plus 1/2 ka squared plus mgc, I'm going to keep all this the same for now, equals 1/2 mv2 squared plus 1/2 kb squared. 1/2 kb squared. That's going to become 1/2 k times b is simply going to be a plus c. And then plus a 0, which we're... actually, I'm going to keep the plus 0 written here for now, just for those who aren't entirely convinced that I can get away with setting h equal to 0 down here, even if it's not the lowest point. I'll use that later to prove a point. And then foiling this, we get a squared plus 2ac plus c squared. So I have 1/2 mv1 squared plus 1/2 ka squared. I probably shouldn't even be bothering rewriting the left-hand side right now, but I'm doing it anyway. Plus, we've got 1/2 k times a squared plus 2ac plus b squared plus a 0. Rewrite one more time, distributing. I have a feeling I'm going to copy a subscript wrong at some point. v2, 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 v1, 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 v1. Yep, so far so good. Plus, we've got 1/2 ka squared plus 1/2 times 2 is just 1, so that cancels out, and then k times ac, k, a, c, plus 1/2 k times b squared is 1/2 kb squared. And then plus the 0 of gravitational potential energy. Okay, 1/2 ka squared cancels on both sides. And then ka over here is equal to mg. Ka is equal to mg. This is basically what I missed last time. And this is where the potential energy is going to cancel out. So I've got 1/2 mv1 squared plus mgc equals 1/2 mv2 squared plus mgc plus 1/2 kb squared plus a 0. The mgc cancels out on both sides. And now we have 1/2 mv1 squared plus, well, plus nothing actually, equals 1/2 mv2 squared plus 1/2 kb squared. And then what was I going to do with that plus 0? I think I missed it at some point. Let me think. If I created like a true lowest position over here and called this distance d and set that to be my 0 height, what would that change? That would make it so that this is mg of c plus d, right? The potential energy, gravitational potential energy up here would become mg of c plus d on the left-hand side of the equation. And on the right-hand side over here, I would have had plus mgd. So on the right-hand side, I would have had a plus mgd. And the mgc still cancels out the same as it did before, but if I set this to be my zero height, then this would have been mg of c plus d, so it would have been mgc plus mgd if you distribute the mg, and then the mgd would cancel out with the mgd that would have appeared in place of this zero over here. So yeah, it doesn't matter, in case you were worried about that. It doesn't matter if I set this height to zero, even though it's not necessarily the lowest point. So that takes care of that potential complication. Now let's get back to over here. So if the place I marked as h equals 0 is the lowest point, then V2 would be equal to 0, which would then mean that all the energy is potential energy on the right-hand side of the equation, which would also mean then that this is the maximum kinetic energy on the left-hand side, which would mean that this would be Vmax, which would mean that this would be Vmax. Actually, regardless of what's going on the right-hand side, since it's only kinetic energy on the left-hand side, this alone means that what you have on the left-hand side is 1/2 mv max squared. Which is not surprising. At the new equilibrium position, you should have the maximum speed, because that's where you have zero acceleration. That's where you switch from speeding up to slowing down, so by definition, you'd have to be at your highest speed where the force is 0. Maybe that doesn't make that much sense. I mean, I did go over it last time. I did draw like a sort of graph explaining the concept. Yeah, over here, right? If you're still speeding up, if you still have some sort of acceleration in the direction of your speed, well, then you're not at your maximum speed yet, because you're still speeding up. So you'd have to wait a little if acceleration is in the direction of your velocity. If acceleration is opposite to the direction of your velocity, well, then you were at your highest speed and now you're slowing down. So then your highest speed would occur when you're neither speeding up nor slowing down, when your net force is at 0. That is when an object will have its maximum speed. Of course, this gets complicated when the forces on an object are changing, and when you have multiple different forces involved, some of which are changing while others might not be, but that's a problem for another day. In this simple case, where the force is 0, where the net force is 0, the speed is a maximum. Anyway, so what we have here then is 1/2 mv max squared, which is also equal to just the total mechanical energy, which is just equal to mechanical energy total, is equal to 1/2 mv2 squared. I'll just call it 1/2 mv squared, a generic arbitrary v, plus 1/2 kb squared. This tells us then that we only need to calculate, B. Oh, man, I messed it up again. Sorry about this. a plus c squared, so that's a squared plus 2ac. How on earth did I end up writing a b here? This is supposed to be a c. Hopefully this will be the last time I screw up this proof. My goodness. Well, at the very least, this serves as another one of those teachable moments where I get to repeat what I've said. I don't even know how many times throughout this course now. You're seeing it right here before your very eyes. There's no such thing as becoming so good at your math and physics that you don't make mistakes, but you can get better at catching mistakes. That should be the goal, and catch the mistakes I did. Okay, so mechanical energy total is equal to kinetic energy plus elastic potential energy measured from this point, measured from the new equilibrium position. And there you go. The gravitational potential energy gets canceled out if you use this as your new x equals 0 position, or I guess technically, since it's vertical, it would be your y equals 0 position. If you use that and measure your elastic potential energy from this point, then gravitational potential energy will just cancel out. And there you go. Now that that proof is out of the way, let's go ahead and look at, I don't even have a proper name for these. I just call them the time functions of simple harmonic motion. The time functions of simple harmonic motion. So we actually kind of derived them already in a way. The true derivation requires calculus, but we can make a little hand-wavy derivation based on what we did back here last time. Last time we compared simple harmonic motion to uniform circular motion, and we saw that the motion, if you just look at one dimension of the motion of an object in uniform circular motion, then you get something resembling simple harmonic motion. It meets all the requirements. Well, I guess it doesn't necessarily meet the energy requirement of simple harmonic motion, but it does meet the first two requirements. The existence of a restoring force that's opposite in direction to the displacement, and also the restoring force is proportional to that displacement. We established that last time when we looked at just the component of the centripetal force that is in the one dimension that we decided to look at. But we didn't really establish the conservation of energy part of it. And, well, if you continue to look at it in two dimensions, you know the energy is conserved because the total kinetic energy stays the same. The total kinetic energy of this object, if it's moving in uniform circular motion, then its kinetic energy stays the same because its speed stays the same. So there's no total work being done on the object if you look at it in the two-dimensional case. Its kinetic energy is conserved in that situation. But when you're looking at it just in one dimension, well, then you could kind of argue that the component of the force the component of the centripetal force that is acting as the restoring force here is kind of a, we'll call it a pseudo-conservative force. Is a pseudo-conservative force. You could treat it as a sort of conservative force, even if it's not necessarily one of the gems: gravitation, electricity, magnetism, or springs, Hookean springs, not non-Hookean springs. Even though it's not one of the gems, it does behave like a conservative force energy-wise. If you look at it and you calculate the work done by it, then you'll see that the work it does is always just determined by the change in position. In this case, the change in x is what we did. It's always determined just based on where it started and where it ended as far as x is concerned. So if I picked, 2 different points on this circle, if I pick this point on the circle or this point over here, and then I pick, say, this as my second point or this as my second point, if I go from here to here, or I go from here to here, or from here to here, or here to here, any one of those 4 transitions, the amount of work done by the force, if you want to take time to actually calculate it, which I guess you couldn't do without calculus because, yeah, it's a variable force at that point. But for those of you who do know the calculus, if you wanted to try and do this, calculate the total work done by the force for these transitions, you'll see that regardless of which of these 2 starting points you use and which of these 2 ending points you use, you'll see that it's independent of path. The work done is independent of path, and it's reversible. So if you calculate it from here to here, or here to here, or here to here, or here to here, if you calculate in the opposite direction, you'll get the exact negative of that work. So that's for you guys who know the calculus. If you want to further convince yourself that this circular motion being viewed from just a single dimension idea is still a kind of simple harmonic motion, for those of you who really want to convince yourselves that this is legit, you can do the calculus and see that it works. But for the rest of us, I just want to go ahead and actually just take these 4 equations that we got last time and maybe modify them a little bit. So I want to just copy these over. I'm going to copy over the drawing. And I'm going to copy over x equals r cosine theta. And then I had v x equals, what did I have? Negative v tangential sine theta. Negative v tangential sine theta. And then I had acceleration centripetal in x is negative a centripetal times cosine of theta. And I guess we can also do force, why not? Centripetal force in x is negative m times the centripetal acceleration in x, so there you go. Okay, and the way I did it was I defined theta as being the angle made with this radius that I've drawn to the right. I could have picked a different starting point, but I'm just going to reuse the same starting point. So this is the starting point, as in this is the point where I start my stopwatch. This is my time starting point. This object is always moving with a constant speed around and around in a circle, and if I decide, if I'm holding a stopwatch and I just start the stopwatch when it's here, that's what these equations are for. If I started at a different point, these equations would be slightly different, and we'll talk about that in a little bit. But let's say that that is our starting point for now. And we said after some amount of time has passed, maybe you see the object over here and it's at this position. And it will have gone through this angle theta. It will be at this angle theta. Okay, so we know this thing moves with a constant speed, which also means it has a constant angular velocity. Right? We know that omega for this thing is constant. Well, if it's moving with constant angular velocity, then we can calculate theta pretty easily. This basically tells us that angular acceleration must be 0. So if we go to our kinematics equations, specifically the second rotational kinematics equation, we get delta theta is equal to omega initial times t plus 1/2 alpha t squared. Well, the acceleration is 0, so that's out of the picture. And then omega initial is just, there is no omega final. Omega initial equals omega final equals omega, equals the same value for the entire motion, so that's just omega times t. And then delta theta, theta final minus theta initial, I'm just going to set theta initial to be 0 over here. But we'll do theta minus, theta initial, I'm going to give this a name. We're going to call it phi. So for right now, phi equals 0 at this point. Just to keep our example simple, we're going to work with a case where phi is equal to 0, and we'll reintroduce it later. But yeah, there you go. Omega t is equal to your delta theta. So that means then theta at any given point in time is equal to omega t plus phi. And that means I can rewrite these equations now. I can say x of t, x as a function of time, is equal to r times cosine of omega t. Actually, you know what? Why not? Let's include the plus phi. I was going to save it for later, but we might as well put it in now. And then Vx of t is equal to negative V tangential sine of that same theta, omega t plus phi. And then acceleration in x as a function of time is going to be negative a centripetal times cosine of omega t plus phi. And we could do the same thing for force, but force is literally just the acceleration equation with an m, so not gonna rewrite all that if we don't have to. Okay, now what about this r, v tangential, and a centripetal? What are those? Well, r is the maximum magnitude for x, right? X is at its highest right at, well, what I chose as my starting point, right at theta equals 0. So R is the maximum value. R can be rewritten as x max. Wait a minute. That's amplitude. Okay, what about V tangential? Well, Vx is at its highest at this point and at this point. Here, all of the tangential speed is in the x direction, and over here as well, all of the tangential speed is in the x direction. In one case, it's negative, and in the other case, it's positive. So V tangential is actually Vx maximum. V tangential, similarly, is Vx maximum. V tangential is Vx maximum. And the maximum speed occurs when? Hold on. Let me think this through for a little bit. I want to see how I would go about proving this. So, Vx maximum. I knew there was something else I should have prepped before I started stream. Oh well. We'll do it live. We'll do it live! Some of you don't know that reference. I'll have to post a link to that video if the video still even exists on YouTube. It's probably been deleted and re-uploaded and deleted and re-uploaded thousands of times. But in case I don't find it, look up Bill O'Reilly, We'll Do It Live, where he just completely freaks out after having to record something during a commercial break that he kept on failing to record properly, and he decided that he would just do it live after the commercials were over. One of the greatest freakouts of all time. But anyway, let me think here. So this Vx max, I want to show that it's related to this x in a way. I think I'll get back to it. Let's first go ahead and say that a centripetal over here, well, this is equal to the maximum acceleration in x. This is equal to the maximum acceleration in x because your centripetal acceleration is always straight towards the center. So when you're up here, for example, centripetal acceleration in x is 0. It's all in the y direction, none of it in the x direction. But when you're at this point or at this point, that's when your centripetal acceleration is completely in x. So that's when, that's the maximum centripetal acceleration you can have in x, when it's just equal to the full centripetal acceleration. When the full centripetal acceleration is straight to the right or straight to the left, that's where you get its maximum value. Either maximum negative value or maximum positive value. Okay, so what I want to do from here is determine how these two are related to x maximum. So what I can say, yeah, I guess it's not easy unless I do try and treat this as a pseudo-conservative force over here. Well, that's okay. That's okay. The important thing for now, we'll do it once we repurpose these equations for springs. I mean, I already said, at least I think I said, that the true derivation of these equations comes from calculus. So maybe it's just that I'm trying to use a non-calculus approach to pseudo-deriving these equations. Maybe that's the reason I'm having trouble here. I mean, I've never actually done this before because usually I just tell my algebra-based students, you know, here are the equations, they come from calculus. This is the first year I've actually attempted some sort of non-calculus approach to deriving these. So maybe I'll get better at it next year. But for now, we're just figuring things out as we go. So if I rewrite these equations now, we have x of t. We have x of t is equal to the amplitude times cosine of omega t plus phi. We have Vx, or I'll just call it v of t for now. V of t is equal to Vmax, well, negative Vmax times sine of omega t plus phi. And acceleration as a function of time is equal to negative acceleration max times cosine of omega t plus phi. By the way, the cosine and sine thing, x of t doesn't necessarily have to take a cosine, and v of t doesn't necessarily have to be sine. It could be the other way around. It could be sine, cosine, sine, depending on what starting point you use and depending on whether you're looking at the x or y part of this. So that's actually kind of flexible. But the pattern you will notice, and it's easier to explain when you know calculus, the pattern you will notice is that it always alternates cosine to sine to cosine. And every time you go from a cosine to a sine, a negative is introduced. So those are the two things to remember. If you start with a sine, you switch to a cosine without changing signs. If you start with a cosine, then the next thing is going to have a sine as you go from position to velocity to acceleration. If you start with a cosine while moving down this list, then not only do you switch to a sine, but you also change from positive to negative or negative to positive. So yeah, the fact that this is cosine and this is negative sine and this is negative cosine, that's not set in stone. That is kind of flexible, and we might see some examples of that later, depending on which problems I end up finding and picking. But this is what we're going to use for any simple harmonic motion that we have. Any simple harmonic motion is going to have an x max, which is the amplitude. It's going to have a v max, which we can determine using energy equations, and it's going to have an acceleration max, which is also where the force is a maximum because, well, that's just Newton's second law, right? Net force equals mass times acceleration. So maximum acceleration occurs at maximum net force. So yeah, these are the equations we're going to have. And let me go ahead and start a new sheet. Let's go ahead and start a new sheet and see what we can do about defining Vmax and Amax. So I'm going to go back to the case of an oscillating mass spring system. Actually, hold on. Let me draw it over here before I start my new sheet. So let's say we've got a mass spring system . And it oscillates between these two positions. So here's x equals negative a, here's x equals positive a, and this is my x equals 0 position. And let's see if we can define Vmax in terms of amplitude, in terms of Xmax. I mean, we already did it last time. But 1/2 m Vmax squared equals 1/2 k Xmax squared, right? If the total energy is all kinetic, then it's equal to this. If the total energy is all potential energy, it's equal to this. Since both of these are equal to the total mechanical energy, they must be equal to each other. If I divide by m, then I get Vmax squared is equal to k over m times a squared, and if I take the square root, then I get Vmax is equal to the square root of k over m times a. Vmax is equal to the square root of k over m, and then that times the amplitude. Square root of k over m. Well, we saw that a lot last time. Where did we see it? Oh, it's on the back side of this page, isn't it? Yep, it is. We saw that last time. The square root of k over m for a spring is omega, the angular frequency. That's just the angular frequency. That's just omega. Square root of k over m is omega. So Vmax is actually omega times a. And now that I've written it, I can actually see it. Oh my goodness. What was I thinking? Okay, so Vx maximum here is equal to, well, V is equal to R times omega. So I guess Vmax would be Xmax times omega. Okay, yeah, omega times A. Okay, I see it now. Good to remember for any future lessons where I teach it this way. Okay, I'm seeing it now. X maximum, or Vx maximum, occurs when you're moving with angular speed omega and you multiply by a distance that is r, which is x max, which is a. Okay, yeah, omega times a. Okay, I'm seeing it now. And then the maximum acceleration is just the full centripetal acceleration, which is equal to, among other things, it's equal to V tangential squared over R, which, if you rewrite V tangential as R times omega, it simplifies to R times omega squared. So yeah, and R is the amplitude, so amplitude times omega squared. Okay. Okay, I thought I was going to have to do something more complicated using energy equations. I was thinking energy-wise, but I didn't have to use energy at all here. I could have just used what I knew from circular motion. Good to remember from next time. I learned something today. Hopefully, you'll be learning something too. Anyway, so Vmax is equal to omega times A, or I prefer to write it with the A first, but, you know, personal preference there. And then the acceleration maximum, well, we just did a kind of proof for the circular motion case, but You could also do it using force over here. So acceleration max occurs when force is a maximum. No, don't want to use green. Hold on. What color should I use here? Let's use this one. So we now have V max is equal to omega times A. And for acceleration max, that occurs when the force is a maximum, and the force is a maximum when you are as far away from equilibrium as possible. Right? When you're either at this point over here or at this point, that's when the force is a maximum. So this is where the force is a maximum, and that's going to be your net force. So that's going to be mass times acceleration max. And that force is equal to, at least magnitude-wise, it's equal to k times x max. It's equal to k times x max, which is k times the amplitude. So k times amplitude equals m times acceleration max. Divide by m on both sides, and we get A maximum is equal to k over m times A is equal to k over m times big A. K over m, well, square root of k over m is the angular frequency, is omega. Right? We just saw that. Square root of k over m is angular frequency omega. So k over m is the square of that square root. So this is omega squared. So A max is actually equal to omega squared times the amplitude. Hopefully I didn't upset anybody by writing this one from right to left. Equal signs work in either direction, so it shouldn't matter. But there we go. So now we can substitute Vmax with omega times A and acceleration max with omega squared times A. This gives us more options when trying to calculate these two values. Now, to calculate Vmax, you no longer have to do some sort of energy equation, and to calculate acceleration max, you no longer have to use force. You still might prefer to use energy and force depending on the problem you're given. This is why I wanted this set of equations to be in a separate stream. So in order to keep these two methods of getting Vmax and Amax separate from one another, here's how I kind of make my immediate decision as to which version to use when calculating them. I will use the version that contains the angular frequency if I am given information about, well, the angular frequency itself, or just the regular frequency, the non-angular frequency, because I can use that to quickly calculate the angular frequency, or if I'm given some information about time. Usually that is where these versions of Vmax and Amax are better used. For other situations where I'm not really given anything about how time or frequency factor into the motion, then I'll just rely on good old energy and force. That's how I separate the two, and sometimes you're given enough information where you could do it either way, and in that case, okay, fine. That works too. If you're given enough information to do things either way, then just do whatever you like, is what I should be saying. I can't do words today. maybe streaming today was a bad idea. All right, now that we have all that written, let's rewrite these equations one last time. It probably won't be the last time, but x of t is equal to a cosine omega t plus phi. V of t is equal to a times omega is how I prefer to write it. You can do omega times a if you prefer. Negative a omega sine of omega t plus phi. And a of t is equal to negative a times omega squared, or omega squared times a, again, personal preference, cosine of omega t plus phi. There we go. And I guess if you want, we can also write force as a function of time. You would just multiply by m. Okay, now why these negative signs, and why the alternating between sine and cosine and sine and cosine? Well, let's have a look at the graphs of sine and cosine and negative sine and negative cosine and compare them to each other. This is not really the most important thing for this chapter, but, you know, just to have the fullest understanding possible of what's going on. Let's say I graph all of these. Actually, I need to make this more symmetrical. Yeah, make it a little, there we go. Probably should bring out the ruler for this, but we'll be fine. Our graphs don't have to be perfect here, they just have to prove a point. Oh God, I messed up this line really badly. Okay, let's take a look at sine, cosine, and the negative sine and negative cosine. Is that what I want? Actually, I think I want to go through the cycle like this. Cosine, and then negative sine, and then cycle down to here is where I would get negative cosine, and then positive sine. Yeah, this is what I want, and we'll cycle through them like this. I don't like the way I positioned that arrowhead. I think I actually prefer it over here. Yeah, there we go. Looping around between these graphs. Let's have a look at what's so... I'm struggling to come up with the right word there. I thought I had a sentence there, but let's figure out what's going on here, is what I'm trying to say. So the graph of cosine starts at its maximum value. The graph of cosine starts at its maximum value, and then 90 degrees later it hits 0. And then 90 degrees after that, it hits, well, the negative maximum value, the minimum value, depending on how you want to look at things. And then 90 degrees after that, it hits 0 again. And then 90 more degrees, it's back to where it started, and then it just repeats after that. And then it just repeats from there. Whoops. that was a little too low. Yeah, there we go. Scribble this out. So that's what the graph of cosine does. The graph of sine, I'm going to write the graph of sine first, or draw the graph of sine rather. It starts at 0. And then 90 degrees later is when it actually reaches its maximum. And then 90 degrees after that, it's back to 0. I probably should have lined these up better. Oh no, I did this wrong. Yeah, I wanted this to, well, okay, we'll pretend that that's lined up. Oh God. Yeah, let's pretend that that's lined up. Okay, let's smoothen that out a little bit. Okay, that'll have to do. And then 90 degrees after hitting 0, it will be at the negative of its maximum. And then 90 degrees after that, it'll be at 0 again. And that's where it will just repeat where it was from the start. These should have been equally sized, perfectly symmetrical and all that, but I messed it up as you saw, so we'll just have to work with this. Yeah, and that's supposed to be a peak there, and oh yeah, I messed this up really badly. Okay, so that's the graph of sine. The graph of negative sine is just this flipped over vertically. So the graph of negative sine is going to look like this. And then that would be one full cycle, that would be 360 degrees. And then it just repeats from there. And then negative cosine would just be the cosine graph flipped. So it would start at the negative of its maximum value. So it would start down here. And then I want to draw these lines ahead of time so that I don't mess this up. So it starts at its maximum negative value and then actually goes up to 0. Then 90 degrees later it goes up to the positive of its maximum value. Then goes down to 0, 90 degrees later. Then goes down to its negative maximum. And from that point on, it just repeats. Yeah, something like this. Okay, so now if we compare these, if my position is, well, let me put it this way. So when position is a maximum, velocity can't be a maximum, right? We already looked at that last time and we saw it again just a few minutes ago, actually, over here. Well, I guess not really, but last time we saw, just using conservation of mechanical energy, when position is a maximum, then kinetic energy has to be zero, right? You put all your mechanical energy into elastic potential energy in the case of a spring, or into gravitational potential energy in the case of a pendulum, and you would have zero kinetic energy. So Vmax cannot happen at the same time that Xmax occurs. So that's why these two can't both be cosine. But also, Xmax occurs exactly when X is 0. So when one is 0, the other is a max. When the other is a 0, the first is a max, or a negative max, as the case may be. I'm using maximum here in terms of magnitude. So the maximums over here between sines and cosines works nicely, because whenever cosine is a maximum, sine is a 0, and whenever cosine is a 0, sine of that same angle is a maximum. Right? Here you've got a maximum, here you've got a 0. Here you've got a 0, here you've got a maximum. Here you've got a negative maximum, a 0. A 0, a negative maximum. A 0, a positive maximum. So when one of them is 0, the other is some sort of maximum. And we see the same thing going on over here, right? Over here you've got, when negative sine is 0, negative cosine is at a maximum. When sine is at a maximum, or when negative sine rather is at a maximum, negative cosine is at 0, and so on and so forth. A 0 here, a max here, a max here, a 0 here, a 0 here, a max here, and so on and so forth. So it makes sense that velocity and position, if one of them is going to follow a cosine pattern, the other one has to follow a sine pattern, or vice versa. The acceleration is going to follow the same pattern as position, because acceleration depends on position, right? That's kind of the whole point of it being simple harmonic motion. Well, not the point, rather, that's the requirement for it to be simple harmonic motion to begin with, is that the restoring force restoring has to equal some negative constant. I called the constant beta last time, but that's not official. That's just the constant that I chose because I couldn't think of a better one. Times the position. And if the force has to be directly proportional to the position, then the acceleration has to be directly proportional to the position. So it makes sense that a of t is going to use the same trig function, sine or cosine, as x of t, multiplied by some constants, of course, because the acceleration and position, while proportional, are not identical, right? That's what this beta accounts for. So, yeah, I guess that covers that. I guess the other thing is, why is it that when we switch from a cosine to a sine, a negative is introduced every time we move from a cosine to a sine? So for that, we would actually need to look at the fact that the sine and cosine graphs are actually the same graph, just 90 degrees apart. If you look at it, the graph of cosine is actually just the graph of sine starting from here. If you start over here, if you start from this part of the graph of sine, you see that's where the graph of cosine starts. So really, the graph of cosine of theta is really just sine of theta plus 90 degrees, or theta plus pi over 2 if your calculator is in radian mode. Theta plus pi over 2 is the equivalent of 90 degrees in radian mode. So degrees, radians. And this is getting into like pre-calculus territory, which isn't the most important thing for physics, but I would hope that you've already learned this before taking AP Physics 1. I know some of you are still in algebra classes, so you probably haven't encountered this yet, but if you have the opportunity to teach yourself this, it can help. It can help you at least accept the equations that we've been looking at today. If nothing else, it gives you comfort, it gives you peace of mind. It demystifies these equations. They stop looking like equations that just got magically conjured up from a parallel dimension out of nowhere. You know, you don't want to be stuck with the whole because my teacher said so mentality. That's no way to learn. But yeah, cosine and sine are actually the same graph, which is why it doesn't matter whether x of t is defined in terms of a cosine or a sine, because all you'd have to do is just shift by the appropriate number of degrees and they're going to be the same graph anyway. That's actually what this plus phi thing does for us. If you add that in, then you can convert any cosine into a sine or vice versa. So that's one thing of note. That's one thing of note, is that a cosine and a sine are really just graphs that are 90 degrees apart in one direction or the other. The other thing to note is if we go back to this over here, if we go back to this drawing. So if I establish that right is positive and left is negative, then we see over here at this point where position is a maximum, is a positive maximum, positive x, we see that, of course, velocity is a minimum. Velocity in x is 0. Vx is 0 at this point. If we just move through theta equals 90 degrees, 90 degrees later, x has decreased to 0, so here we have x equals 0, and velocity is a negative. We have a negative velocity over here. So actually, for this whole quarter of the circle, the velocity was in the negative direction and continues to be negative. So I guess what I'm trying to say is, if we slice this circle into 4 sections, let's actually redraw the circle over here. So if we slice that circle into 4 sections, and again, we're just concerned with what happens in the x dimension, not the y dimension. We're just looking at the motion between these 2 points. If you want to do it in the y dimension, then you can feel free to do that. It's not really going to change anything. You're just going to basically be renaming your variables. Basically, all you'd be doing is that. So if you want to do it in y, be my guest, but x is good enough for us. So where was I? So if we wanted to cut this into quarters, then what we have, this is going to be positive a, that's going to be x equals 0, that's x equals positive a, that's going to be x equals negative a. So we're looking at 4 different quadrants. Over here in this quadrant, except of course at the extremes, we would have x is positive, and velocity is going to be in the negative direction. The velocity component Vx is, whoops, negative. Accidentally wrote positive there. We have a negative Vx, and the x component of the acceleration is negative. So Ax is negative. That's all in this quadrant. What about in this quadrant over here? Well, here, x is negative. Vx is still negative. Vx is also negative. It's still, we're talking about an object that's circling this way, by the way. I forgot to mention that. And the acceleration is actually going to be in the positive direction. Ax is positive here. Right, the centripetal acceleration is towards the center, and in this quarter, towards the center means that it has a component to the right. So as far as x is concerned, we've got a positive acceleration. Down in this quarter, well, x is still negative. It's left of center. Vx is actually positive here. When you're moving along this direction, now you're actually moving with some component to the right. So we have a positive Vx, and we have a positive Ax still. Acceleration is still towards the center, is still going to have a rightward component to it. And when we get to this last quarter, what do we have? Well, x is positive again here. Now we're to the right of the center. Vx is back to being negative, because now if you're moving over here, actually, no, wait. No, Vx is still positive. You're still moving to the right. Yeah, so Vx is positive. And acceleration in x, that's what changed. Acceleration in x is negative. So x and Ax, whenever they change together. Here you had positive x, negative Ax. Here you have negative, positive. Here you've got negative and positive. And here you've got positive and negative for acceleration in x. X and acceleration in x always change together. When one of them changes, the other one changes too, and they're always opposite of each other. But Vx has a different pattern. Vx seems to change a little bit late. So when we went from this quarter to this quarter, x and Ax changed, Vx didn't. Vx changes 1 quarter later. Vx is 1 quarter late compared to x and Ax in changing signs. It's 90 degrees late, you could say, in changing. So if x is defined by a cosine, then 90 degrees late means what? If x is defined by a cosine, then Vx has to be defined by a sine. It changes from, let me see, where's the change from positive to negative for cosine occurs over here. Change from positive to negative for speed occurs, well, actually it should be negative to positive. Change from negative to positive for speed, for velocity, actually occurs over here. Wait a minute. So actually, I think I have it the other way around. It's the speed changes signs 90 degrees early. Yeah, because this is where speed changes signs. If your position is defined by a cosine and it switches from positive to negative here, no, wait. I think I've confused myself. Give me a minute to recollect my thoughts. I know I'm close. I'm just, I'm talking faster than my brain can think. Or maybe it's the other way around. So if I were to, let me see, negative, negative, positive, positive versus positive. So speed, if I look at what speed does compared to just x, I just want to look at it compared to just x. Speed is at 90 degrees ahead or 90 degrees behind. If I were to move this over, if I were to move this over 1/4 and then this over 1/4 and then this over by 1/4 and this over by 1/4. Don't listen to me, I'm just talking to myself here. Trying to convince myself before I try to convince you. Then that would be positive and positive, negative and negative. They would be aligned if I moved it 90 degrees forward, which means then that Vx is 90 degrees behind. It takes 90 degrees later. Okay, so Vx is 90 degrees behind x. Vx is always 90 degrees behind x. Regardless of whether it's positive or negative, it's 90 degrees behind x. So whatever x does, let's say x is doing this, if x is doing this over here, then Vx does the same thing 90 degrees later. So Vx would be when x, whatever x is doing at its 90 degree mark, Vx does at 0. And then whatever x is doing at 180 degrees, Vx does it at 90, and so on and so forth. So Vx is equal to some constant. Let's call it, let's just call it c. Hold on, let me think here. No, how do I want to do this? Yeah, is some constant times is going to be some constant times x shifted by 90 degrees. How would I write that mathematically? Come on, brain, catch up. So if so what I want to do is say if x equals some function of theta, some trig function of theta, then Vx is equal to, forget this, Vx is equal to some constant times that function of theta, and then would it be plus or minus 90 degrees? Vx is equal to some constant times that function times theta. it would have to be, let's see, if x is a cosine, for example, then Vx would be a negative sign. So cosine of 0 is that value. Vx at 0 is taking cosine of negative 90. Or no, wait, no. Vx would be cosine of positive 90 rather. So it would be plus. It would be plus. Okay, there we go. So Vx is equal to some constant times whatever function x is using with a 90-degree shift, with a plus 90 degrees. Okay, so then if I look at whenever x is a sine versus a cosine, let's see what that plus 90 degrees does for us. We already said cosine of theta is equal to sine of theta plus 90 degrees. So give me a minute here. I know I'm turning this into a sort of pre-calculus lesson, but I think it might be worth it. I didn't plan this, which is a bit of a problem, but we'll figure it out. So if x is a cosine, then it's basically already a sine plus 90 degrees. So if we're going from a cosine to a sine, we always throw in a negative because cosine of theta plus 90 degrees is equal to negative sine of theta. Is that right? Let me draw the graph of cosine of theta plus 90 degrees. So cosine of theta plus 90 degrees. Cosine of 0 plus 90 is cosine of 90, which is 0. Cosine of, at our first 90 degree mark, cosine of 90 plus 90, that's cosine of 180, which is negative 1, so that's the negative max. Cosine of 180 plus 90 is going to be cosine of 270, which is 0 again. And then cosine of next 90 degrees, cosine of 270 plus 90, that's cosine of 360. That's the same as cosine of 0. That's the maximum. Okay, and it looks like that. And yeah, that is indeed the graph of negative sine. There we go. So cosine of theta plus 90 degrees is what I have graphed here, where my horizontal axis is theta. And yeah, the graph of cosine of theta plus 90 degrees is equal to negative sine. And of course, that would also mean that the graph of negative cosine of theta plus 90 degrees would be equal to positive sine. Okay, there it is. We finally got that out of the way. Sorry for the long detour, but hopefully for somebody out there, it was helpful. Now, let's get back to wherever we started this detour from. So what we've established basically now is that you can, depending on your starting point, depending on whatever point in the simple harmonic motion you actually, start your timer, you start your stopwatch, you could define x in terms of a sine or a cosine or a negative sine or a negative cosine. But the pattern, once you've decided which trig function you want to use for defining your x, the pattern will always be alternating between sine and cosine. And if you're going from a cosine to a sine, you also throw in a change of signs. You change a positive to a negative or a negative to a positive. So, for example, another possible set Why is this pen giving up on me today? There we go. Another valid set of equations is you could have x of t equal to, you could have it equal to negative sine of omega t plus phi. And then you would get v of t, well, I should say negative amplitude times sine of omega t plus phi, and then v of t would be, well, sine switches to cosine without changing the negative, so that's going to be negative a omega cosine of omega t plus phi. And then acceleration, now that we're switching from a cosine to a sine, we have to throw in a negative because of that 90-degree shift. So acceleration as a function of time will be, we switch from negative to positive, we get positive a omega squared sine of omega t plus phi. This would be a better set of equations to use if you started, let's see, if you started down here. If this was your starting point, if you start here and move counterclockwise, then this set of equations would probably be what you derive if you did things the way I did last time over here. This is probably what you would end up with. And yeah, it's all valid. It's all perfectly valid. Or you don't even necessarily have to start here. You could start, a few degrees off if you really wanted to. But I guess then your theta would be what? Your theta would be defined relative to this line, if I'm not mistaken. And then you would just define theta opening counterclockwise from there. I believe that's right. Because, yeah, if this is theta, then for your first few values of theta, sine of theta would give you this component. Yes, it would give you this component, which, as you can see, is the x. Yeah, there it is. So yeah, it just depends on where you want to define, like, the starting point for your object and your theta. But depending on how you define things, you might get a sine here or a cosine here, but the pattern remains the same. Cosines switch to sines and sines switch to cosines, and when cosines switch to sines, you also change from positive to negative or negative to positive. That is much easier to explain when your students already know calculus, because then you can just tell them that v of t is the derivative of x of t, and a of t is the derivative of v of t, and the derivative of sine is a cosine, while the derivative of cosine is negative sine. But unfortunately, you algebra-based students out there don't have that luxury, so I hope this was sufficiently convincing for those of you who just really needed to be fully convinced on this. Now that we've got this out of the way, let me check my notes and see if there's anything else I want to do before I look at some problems. Well, we have the physical pendulum, which I will deal with later. Let's look at some problems first. Let's look at some problems, and then we'll talk about the case of the physical pendulum. Do I have? Yep, I've got a backside here, so let's use it. All right. Let's find ourselves a good time function problem. An object moves uniformly around. No, we don't want circular. I think we've had enough of circular. The frequency of vibration of an object spring system, or mass spring system as I like to call it, is 5 Hertz. When a 4-gram mass is attached to the spring, what is the force constant of the spring? Okay, so this is basically what you guys were doing for homework from last time. Let's do it real quick. It says frequency of vibration is 5 Hertz. And the mass was 4 grams, which is 0.004 in kilograms. Oh, and I just remembered one other thing that I forgot to do last time. Let me put it on my notes. And we'll do it after this problem. So mass is 4 grams, which is 0.004 kilograms, and they wanted us to find the force constant of the spring. Find K. Okay, so here we would use the equations that we wrote at the end last time. So I'll do period equals 2 pi square root m over k, and then take the reciprocal of that, so frequency is 1 over the period equals 1 over 2 pi times 1 over square root m over k is square root of k over m, and plug in the numbers and solve for k. Okay, so we have 5 Hertz is equal to 1 over 2 pi times the square root of k over 0.004. If I multiply by 2 pi and then square both sides, so you have 10 pi equals square root k over 0.004. And then square both sides, so you get 100 pi squared equals k over 0.004. By the way, mental shortcut, I don't recommend you do this on free response, but if it's multiple choice and you don't want to bring out a calculator If you want to do just a quick calculation, pi squared is kind of equal to 10. I mean, you can do it on your calculator right now if you want. Pi squared is 9.8696. So actually, not only is it kind of equal to 10, it's also kind of equal to g. Pi squared is kind of equal to g, the 9.8 that we've been using for gravity. So don't overuse this. Do not overuse this. Use this. Don't write it down on your paper, but use it as a mental shortcut for when you just want to quickly determine, if it's a multiple choice question and you just want to quickly see which one is the closest answer. That is probably the only circumstance where I would try and use this. But if you write this like on your free response, you're losing points. Don't do it. Don't do it. Just use it for like very quick check to see if your numbers make sense for checking your work, or use it for multiple choice when you're just trying to quickly see which number of the numbers you're being presented with is actually the closest to being correct. I know I've mentioned it before, but here it is again. Pi squared is approximately equal to g, which is approximately equal to 10. A little bit of a shortcut to use very sparingly. Anyway, multiply 0.004 over, and yeah, 100 pi squared is almost 1,000. So 4 1,000ths times almost 1,000. K should be almost 4. 100 pi squared times 0.004, and I get 3.9478. 3.95 is what I'll say. And that's going to be newtons per meter. So you saw what I just did. I used it only to make sure that my answer was close to what it should be. If I had gotten something way different from 4, then that would hopefully cause alarm bells to ring in your mind and go, wait a minute, something went wrong. Okay, so before we look at our next problem, something I forgot to do last time. I even said as much. I even said I would probably forget to do it, I think. Or maybe I said if I remember to do it, or something along those lines. I forget. But something I said I was going to do last time and completely forgot to do at the end was check the units for our period and frequency equations. Do the units work out? Well, fortunately, since period and frequency are just reciprocals of each other, all I have to do is prove it for one, and I've automatically proven it for the other. So let's see if t equals 2 pi square root m over k for springs, or t equals 2 pi square root L over g for pendulums actually works. Oh, and by the way, even though pendulum ends with I think I forgot to comment on this, the plural of pendulum is not pendula, surprisingly enough. I mean, I already talked about how the plural of momentum is momenta, and what else did we have? Was that the only one? It's the only one I can remember off the top of my head right now. But yeah, after all of that ranting about irregular plurals, turns out the plural of pendulum is pendulums, not pendula, for some reason. There used to be a time in history, apparently, where the plural was pendula, but I think it's now just outdated. So yeah, pendula is incorrect due to, I guess, going extinct, linguistically speaking. Just something that I felt like commenting on. Anyway, let's go ahead and look at these two equations and see if the units that we get over here are actually units of time. And if they are, then no point in redoing it with the frequency equation, because you would just be flipping over the units here and getting, well, flipped over time units. Once you've done one, you've done both. So the 2 pi doesn't really matter, but units of period should equal the square root of the units of mass over units of spring constant. We'll do this one first. So units of mass, that would be kilograms, over the units of the spring constant are newtons per meter. And newtons per meter, well, I can multiply top and bottom by meters and get meters to cancel out from here, so I get kilogram meters over newtons. And a newton is what again? If we look at something like net force equals ma, we get newtons equal kilograms times meters per second squared. So it's kilogram meters per second squared, and some of you can already see what the second squared is going to do. So that equals the square root of kilogram meters over kilogram meters per second squared. Oh, kilogram meters cancels with kilogram meters, and then 1 over second squared is equal to second squared is equal to the square root of second squared is equal to seconds. Ah, so we do indeed get seconds for our units of period over here, as they should be. Okay, what about doing it again, but for the case of the simple pendulum? So units of period need to be equal to the square root of units of length over units of acceleration. So that's going to be the square root of meters over meters per second squared. Oh, this one's even easier than the previous one. We don't even have to introduce kilograms here. Meters cancel with meters, and you've got 1 over second squared. 1 over a fraction is just the reciprocal of that fraction, so that's just going to equal the square root of second squared is equal to seconds. And there you go. So yeah, the units are correct. That gives us further confidence that our derivation from last time was legit. It's not an outright proof, but it gives you some comfort that at least some part of it was done correctly. Now then, back to questions. Back to practice problems. This one says a spring stretches 3.9 centimeters when a 10-gram object is hung from it. The object is replaced with a block of mass 25 grams that oscillates in simple harmonic motion. Calculate the period of motion. Okay, so they're using the 3.9 centimeters for 10 grams is just so that you can figure out, so they didn't say it outright, but the implication here is that a 10-gram object was hung vertically from the spring, and then at 3.9 centimeters is where the spring needs to stretch in order for that 10-gram object to hang still on it. So that lets you do, let's use orange, that lets you do K times, I guess, KY is equal to mg. That's where the spring force and the weight of the object cancel out, and that allows you to calculate k because you're given the y and the m and you know the g. And then they tell you that a new mass is attached to it of 25 grams, and they want you to calculate the period. So you will have found k, and you will have been given the new m, and then it's just 2 pi square root m over k, and you're done. So I won't do that one, but that's how you would do it. Not that. What about this one? Placed on a frictionless horizontal track. Spring constant. Okay, well, I guess this isn't the hardest problem ever, but what could make it hard is just interpreting it correctly. So it says a cart of mass 250 grams is placed on a frictionless horizontal air track. A spring having a spring constant of 9.5 newtons per meter is attached between the cart and the left end of the track. When in equilibrium, the cart is located 12 centimeters from the left end of the track. So this is where students might get confused by this problem, because they'll think that this 12 centimeters is the amplitude or something like that. It says then, if the cart is displaced 4.5 centimeters from its equilibrium position, find the period at which it oscillates, its maximum speed, and its speed when it is 14 centimeters from the left end of the track. So you've got a track, and then you've got they said its equilibrium position is 12 centimeters from the left end of the track. So this is 12 centimeters. And then they say the cart is displaced 4.5 centimeters from its equilibrium position. They don't say whether it's to the right or to the left, but this is our x equals 0 position. And then 4.5 centimeters either this way or this way. Is how it gets pulled or pushed, and then it's released and starts oscillating back and forth between these two positions. So the 12 centimeters is kind of a nothing burger here. Kind of. It's still relevant for answering that third question that they've asked. So it says find the period at which it oscillates. That's just going to be 2 pi square root m over k. They gave you m is 250 grams, which you would want to convert to kilograms. And they gave you k is 9.5 newtons per meter. That is already in its standard units, so no need to convert that one. And yeah, it says find the period 2 pi square root m over k after conversions are done. And then B, find its maximum speed. You can just use energy for that. You can just do 1/2 mv max squared equals 1/2 k x max squared. X max, or A, is going to be your 4.5 centimeters. Convert that to meters, of course. And then part C, find its speed when it is 14 centimeters from the left end of the track. That's just another energy question. So when it says 14 centimeters from the left end of the track, that means 14 centimeters from here. Let me do a different color for it. That means 14 centimeters from here. And if you're not on top of your geometry, this is where you will screw things up. That means, wait, no, I drew my 14 centimeters wrong. Looks like I'm not on top of my geometry. Okay, over here, somewhere over here. That's better. That's 14 centimeters. This is 12 centimeters. 14 centimeters is 2 centimeters away from equilibrium. That's what you want. What you want is to realize that this just means 2 centimeters away from equilibrium, and then from there you would just use conservation of energy. You would say, I would compare either to the equilibrium position or to one of these extremes. It doesn't matter which one you use, but those would be the easiest ones. So you could either do 1/2 mv max squared equals 1/2 mv squared plus 1/2 k 2 centimeters squared, converted to meters would be 0.02. You could either do this, or instead of setting it equal to 1/2 mv max squared, you could also set it to 1/2 k a squared, which is actually what I would prefer here, because Vmax is something you have to calculate, and if you make a mistake when calculating it and then you reuse it over here, then now one mistake has turned into 2, and that's 2 points lost instead of 1. So from a risk management perspective, I would prefer this one, but you can use either one of these and set it equal to this in the middle and solve for the V. But yeah, you've seen that stuff before. We don't need to dilly-dally with this one. Oh, here's an interesting one. This is really just knowing your equations. Oh yeah, speaking of which, equations. So the equations that I gave you here. Like with most equations, memorize these. Memorize them. I don't know if, actually, I don't think these are on the AP exam formula sheet. These might be one of the few equations that are not on the formula sheet, but I could be wrong. I'll have to take another look at it and double check. But whether they're on the sheet or not, memorize them. You don't need to memorize this because you should know net force equals ma and be able to get it just from knowing this one. But yeah, commit these to memory. These are more pattern based because, like I said earlier, we could have the x be proportional to a sine function instead of a cosine function. So don't memorize the functions necessarily, but just memorize kind of the format and the pattern. Memorize the format and the pattern here. Anyway, back to this. So it says the motion of an object is described by the equation x equals 0.3 meters times, I guess they wanted to include the units because technically if this was in centimeters it would still work, or inches or whatever they wanted to use, times cosine of pi t over 3. So what we see here is that they are describing the angle in radians, and this is pretty much the only chapter where you need to convert your calculator to radian mode if you're using these equations. If you're using these time functions, your thetas and phis and omegas need to be in radians. They need to be in radians. You need to use your calculator in radian mode when doing this. So if you get this on your exam where you have to bring out the calculator. Hopefully you don't have to do that for the multiple choice. And then for the free response, I would save that question for last, because if you do it first and you leave your calculator in radian mode, you forget to switch back to degrees, and then you go and do other questions, oh boy, are you going to mess up something. So yeah, I would save the only situation that demands radians on your calculator mode. I would try my best to save that for last, or be very, very careful about switching your calculator back to degree mode after doing it. Those are your two options. Either do it last so it doesn't matter if you forget, or just don't forget. I mean, I've already been saying for a while, I don't remember how many episodes ago it was when I first said it, but get in the habit of just every time you press the on button on your calculator, press the mode button too. I know it seems silly, but one day this could save you, because one day it might make you pause and go, wait a minute, I'm in radian mode. I shouldn't be in radian mode. I should be in degree mode, or vice versa. So yeah, just get in the habit of on mode, on mode, on mode. Every time you press that on button, develop this subconscious habit of pressing the mode button. Most of the time, you're just going to put yourself on a screen that you didn't even need to be on, but the one day that you need to see that screen, it'll be worth it, because it'll save your grade, probably. Anyway, so it said, the motion of an object is described by the equation x equals 0.3 meters times cosine of pi t over 3. Find the position of the object at time 0 and time 0.6. So, first thing is find the position x at time 0 and the position at time 0.6 seconds. X of 0 and x of 0.6. That's pretty easy. You just plug in 0 and you plug in 0.6. This is just calculator work. So x of 0, well, pi times 0 over 3 is 0, and cosine of 0 is 1, and 0.3 times 1 is 0.3, so that'll be 0.3 for x of 0, 0.3 for x of 0, and for x of 0.6 I actually need my calculator now. So in radian mode, I'm going to do it right in front of you. In radian mode, you do 0.3 times cosine of pi times 0.6 over 3, close parentheses, and I get 0.243. I get 0.243 meters, approximately. Is 0.243 reasonable? Yes, because it's less than the amplitude. It's less than 0.3. If it was more than 0.3 or less than negative 0.3, if its absolute value was more than 3, then that would mean a mistake occurred somewhere. And now I'm going to switch back to degree. Well, actually, no. I'll keep it in radian mode for now, because we're probably going to have more questions like this. So I'll keep my calculator in radian mode for the time being. But yeah, find the position at time 0 and time 0.6. We did. Find the amplitude of the motion. Just 0.3. This is just pattern matching. Amplitude equals 0.3 because, well, look at how they've written their equation. X of t, the pattern is amplitude, maybe with a negative sign, times some trig function. In this case, they chose cosine, times omega t plus phi it looks like there is no plus phi here, so phi is equal to 0 for theirs. But yeah, amplitude is just the thing in front of the trig function is equal to 0.3. Okay, so that's the second part of it. And then part C, find the frequency of the motion. Find the frequency. Part C, find frequency. Okay, well, frequency is most directly related to angular frequency. Angular frequency, one of the formulas from last time, is angular frequency equals 2 pi f. And we can get the angular frequency from here because just pattern matching. Amplitude was 0.3 and then cosine omega t. So what am I multiplying t by? It looks like pi over 3 times t. So pi over 3 is my omega. Omega must be pi over 3, just matching the pattern here. The thing multiplied by the t must be the omega. So omega is equal to pi over 3, which, and that's in radians per second. And if I multiply, or no, rather if I divide by 2 pi, right? If omega is 2 pi times frequency, then frequency is omega over 2 pi. So frequency equals omega over 2 pi equals pi over 3 divided by 2 pi. The pi's cancel out, and we get 1 over 3 over 2, that's 1 over 6. 1 over 6 hertz. 1/6 of an oscillation per second. In other words, it takes 6 seconds for a complete oscillation of this thing. It takes 6 seconds to, wherever it starts, to, I guess it would start fully stretched. So it would take 6 seconds to go from fully stretched to coming back, passing the equilibrium, going to the left, coming back, passing equilibrium again, and then going all the way back to the right. It would take 6 seconds for all of that before a full repetition of the motion were to occur. So that was part C, and then part D says, find the period of the motion. D, find the period of the motion. Well, we found frequency, so just take 1 over that. I guess I answered it just now with that little mini tangent. Period equals 1 over frequency. So just 1 over 1/6. 1 over 1/6 is equal to 6 seconds. Done. And I guess circle my answers. And yeah, there's that, and there's those. All done. Let's see what else we have here. Is this a good problem? 2 kilogram object, frictionless horizontal track. We're given K. We're given A. Ooh, actually, this is a good one. Okay, let's do this one. So this one says, actually I don't want to do green. Let's do, I guess I haven't used pink in a while. It says a 2 kilogram object on a frictionless horizontal track is attached to the end of a horizontal spring whose force constant is 5 newtons per meter. The object is displaced 3 meters to the right from its equilibrium position and then released, initiating simple harmonic motion. So first it says, what is the force, magnitude, and direction acting on the object 3.5 seconds after it is released? And then second part is asking, how many times does the object oscillate in 3.5 seconds? So it's asking about force, and it's giving you the amount of time. It's asking you for force at a specific time. This calls for using the time functions instead of using your regular force and energy equations. And that's the whole reason I chose to do this in the first place, just because of that. When you see mention of time and frequency and period, well, maybe not necessarily frequency and period. I guess it depends. Let me think here for a second. Because I'm trying to go back to what I said earlier about how to decide whether to use, the time function approach or whether to use the more traditional approach of using force and energy for solving for certain things like maximum speed and force and whatnot. What clues you in on which approach to take? Yeah, I'm blanking on what it was I wanted to say, but I feel like I had a comment to add to that just now, and I've lost it. Oh well. If it's that important, I'll remember it later or post it in a pinned comment or something. Anyway, this one directly mentions time, and the only functions we have that mention time are, well, these time functions that we've introduced today. So this one definitely calls for this new set of equations and not the older set that we were working with last time. So let's see, mass was given as 2 kilograms. I guess I should just draw the situation. A drawing we've seen many times, I know. Frictionless track, of course, because if there's friction here, it's not simple harmonic motion anymore. 2 kilogram object, frictionless horizontal track. Force constant is 5 newtons per meter. K is 5 newtons per meter. The object is pulled 3 meters to the right from equilibrium, then released. Okay, that's the amplitude. That's X max is 3 meters. And then part A, what is the force, magnitude, and direction acting on the object 3.5 seconds after it is released? So A, what is the force at 3.5 seconds? After release? And then part B, how many times does it oscillate in those 3.5 seconds? B, how many oscillations, cycles, repetitions, whatever you want to call them, in 3.5 seconds. Okay, so for force, I would just do mass times acceleration. So acceleration as a function of time is going to equal, well, a positive or a negative amplitude times omega squared times some trig function, sine or cosine, let's say sine for now, of omega t plus phi. I'll just call it theta for brevity's sake. Is it impossible if we don't know whether it's a sine or a cosine here? No, not really. Actually, wait a minute. I'm thinking of a different problem. I'm thinking of a different type of problem. Here it actually does matter. So they told us that they started with stretching it. So they started at x equals positive a, and that's also where we start the timer, so phi is going to be 0. By the way, I forgot to comment on this, but the phi in omega t plus phi, this phi over here is called the phase angle, or rather the phase shift, I should say, is called the phase shift. So if you come across that term, that's what they're talking about. If you see that in a textbook somewhere. And the whole thing, omega t plus phi, would be called the phase angle, because it's the angle that tells you what phase the object is currently in its simple harmonic motion. Yeah, I don't usually use that terminology. I usually don't have much reason to. But if you see it in your textbook or in a YouTube video or something, now you know. So we were doing, let's see, so we start with this thing stretched all the way out. So actually we do need to find x of t is equal to amplitude times, so it's going to start at positive 3 and then decrease while still being positive for a while, and then it'll hit 0 and then it'll go negative. Starts positive and then goes negative, huh? Starts at the maximum and then goes down. That's a cosine. Cosine starts at a maximum and goes down. If it started at a minimum, if it was pushed to the left and then released, then that would just be negative cosine. So it would start at the negative maximum. So yeah, if it starts at one of the amplitudes, then your x is going to be a cosine function. If it starts at the equilibrium position, your x is going to be one of these sine functions, because sine starts at 0, cosine starts at a positive or negative maximum. I say negative maximum, your textbook might say minimum, all the same thing, but I feel like negative maximum is less confusing here. Anyway, amplitude times cosine times omega t plus, well, there is no phase shift, because you don't start, at some awkward place in the middle of the motion. You start at one of the key positions. You start at maximum amplitude. If you start anywhere other than the equilibrium position or negative A or positive A, that is when you're probably going to have a phi, if you start the timer at a position in between these lines and not at them. But usually they will keep it simple and just have a phi equals 0 in most situations. Anyway, a cosine omega t plus our phi over here is just going to be 0. So it's going to have the form a cosine omega t. Okay, that just means then that the speed, the velocity, is going to have the form negative a omega sine omega t, and most importantly for us, the acceleration, and by extension the force, is going to have a negative a omega squared cosine omega t pattern to it. So we need to find, we already know the amplitude, it's 3. We need to find omega, which we can easily do. It's just the square root of k over m. And we can plug in t is 3.5 seconds and then multiply by the mass and we're done. Okay, so a of 3.5 is equal to negative 3 for the amplitude times omega squared. So omega is square root k over m. Omega squared is just k over m, is 5 over 2. 5 over 2. K is 5, M is 2. Times cosine of omega t. That's square root of 5 over 2. Times t is 3.5 seconds. Remember to be in radian mode when you do this. So I'm going to do -3 times 5 over 2 times cosine of square root of 5 over 2 times 3.5. And I'm getting -5.49. I'm getting -5.49 meters per second squared. Multiply this by the mass, multiply this by 2 kilograms, and I get -10.98. So force at 3.5 seconds equals -10.98 newtons. The negative just means it's opposite in direction to the displacement, which should mean if I plug in 3.5 into x of t, it should mean that x of t is positive. So if I go ahead and actually do that, if I do positive 3 times cosine of the square root of 5 over 2 times 3.5. I knew I was forgetting something. Then I get 2.196. I would round that to 2.20, but yeah, you would be at 2.20, so about 2/3 of the way. It would be somewhere around here at that moment in time. So yes, it does make sense for the force to be in the negative direction. So yeah, what is the force, magnitude, and direction acting on the object? I would just report this as 10.98 newtons to the left. Don't say negative. Tell them on your exam, in your answer, what your negative sign means. Tell them that negative means left. Or I guess you could just report it as negative and start the problem off by writing a little note for the graders indicating that you've chosen right to be positive and left to be negative, but you know me, I've said this, I don't even know how many times at this point. Just state the direction in words. Don't rely on positive and negative signs. It reduces confusion, and the less you confuse the person grading your stuff, probably the less they will get mad at you and maybe potentially not take points off of you on purpose, because they would get in trouble for that, but they might be less inclined to pay full attention to your work, and they might miss something here or there and make a mistake. I think the way that grading works, though, they have more than one person grade your work, and then they just kind of... Actually, I'm not entirely sure. I'm not entirely sure off the top of my head what the exact grading process is, but I'm pretty sure they do have more than one set of eyes look at it just to ensure accuracy. Anyway, part B says, how many times does the object oscillate in 3.5 seconds? So this one might throw people off, but it really shouldn't. If you know how much time it takes to complete a full repetition, then once you know how long you've been going, you can count the number of repetitions that have occurred. So all I have to do is calculate period. So period equals 2 pi square root m over k. So 2 over 5, 2 pi square root of 2 over 5. Which is about 3.97 seconds. About 3.97 seconds. And that then tells me that this thing hasn't even completed a full cycle yet. At 3.5 seconds, it hasn't even completed a full cycle. It's close to completing a full cycle. And also it is consistent with what I said earlier, that it's somewhere here. It's on its way back to the right. Its velocity would have to be rightward at this moment in time. So yeah, consistent with what we did in the previous part. 3.97 seconds. How many cycles has it completed then? 3.5 divided by 3.97. 3.5 seconds divided by 3.97 gives me 0.88. It has completed 88% of a full cycle. So 3.5 over 3.97. This isn't, some sort of new equation that you need to memorize. This is just, mathematical reasoning skills. I would hope that you don't need me to give you another formula to memorize for this. I would hope that you'd be able to piece together amount of time that passed divided by the amount of time per repetition, the period, equals the amount of repetitions. I would hope that you could just common sense your way into recognizing that you need to do that. Because if you can't, then perhaps a math review is in order before you do any more physics. Put your physics studying on pause and go back and work on math. 0.8816, I'll say 0.882 cycles, repetitions, oscillations, whatever you want to call them. And that's that problem done. There was something I remembered in the middle of doing that I forgot to put on my notes. What was it? Hold on, give me a second here. There was something. Oh, right. Gotta make sure to comment on that. Writing it down now so that I don't forget to talk about it later. I actually forgot to prep for that, so we'll see. I might mess up another explanation later. Okay, so we've done a couple of examples here. It's all been springs so far. I would like to do a couple of pendulum ones. Let me read this one real quick and see if it's a good problem. If not, then I'll skip to the pendulum section and see what's in there. Spring of negligible mass. Okay. 0.5 kilograms. Frictionless surface as always. Find the force constant. We know how to do that. Angular frequency, frequency and period. I think we've done enough of that. And determine position at a specific time. Yeah, we've already done something similar right here with this last problem. Okay, we can skip that one. Let's take a look at some of these pendulum questions then. Here's one that says, a man enters a tall tower needing to know its height. He notes that a long pendulum extends from the ceiling almost to the floor and that its period is 15.5 seconds. How tall is the tower? And if this pendulum is taken to the moon, where the free fall acceleration is 1.67 meters per second squared, what is the period there? Is the backside of this used? Yes, it is. New sheet time. So, man enters a tall tower. He notes that a long pendulum extends from the ceiling almost to the floor. So we've got a long pendulum. We're assuming a simple pendulum, of course. If it was a physical pendulum, we'd have more information. And he notes that a long pendulum extends from the ceiling almost to the floor and that its period is 15.5 seconds. Period is 15.5 seconds. How tall is the tower? Well, that's basically asking what's the length of the pendulum string, because the height of the tower would just be the length of the string when it's in the lowest position, when the pendulum is in its lowest position. So yeah, this is going to be the height of the tower, which equals the length of the pendulum string, which equals this L. And then part B, if this pendulum is... Okay, we'll deal with that later. Part A first. Part A, how tall is the tower? What is L? You might think, because we don't know the mass, that there's an issue here, but there's really not, because mass doesn't factor in. The mass cancels out. We saw that last time. We saw the mass getting canceled out when we derived the period equation for a pendulum. So period equals 2 pi square root L over G is the period equation for a pendulum, and we know G. It's 9.8. Unless you're told otherwise, assume that the G to be used is just the G that we already know, G on Earth's surface, which is 9.8, give or take. So 15.5 equals 2 pi square root L over 9.8. We have enough information here to solve for L. 15.5 over 2 pi. Square both sides, so I'm going to do 15.5 divided by 2 pi. And then whatever that result is, I'm going to square it, and that's going to be L over 9.8. So L over 9.8 equals 15.5 over 2 pi squared, and then multiply by 9.8 and you're done. Multiply by 9.8, and I'm getting 59.6389. I'm going to round that to 59.64. L is about 59.64 meters. The tower is about 60 meters tall. Part B said if you take it to the moon, what is the period there? Part B, period of the same pendulum, but now on the moon. Well, now that we know its length, we can just plug it in. It's going to be, whoops, wrote the square root a little too early there, 2 pi square root, the length, now we know, is about 59.64 over g on the moon is 1.67. And plug in your numbers and we get 2 pi square root 59.64 over 1.67 is about 37.55 seconds. 37.55 seconds. Makes sense to me. Weaker gravity, slower swinging of the pendulum. Note that mass does not matter for a pendulum, at least for a simple pendulum. The mass does not matter. Similarly, they might ask you a trick question where they take a spring to another planet and ask you how its period or frequency change when you move it from Earth to Mars to the moon. For a spring, nothing is going to change if you change planets. The period and frequency equations tell us as much. Period and frequency for a pendulum depend on mass and spring constant only. The acceleration due to gravity is not a factor. Even if we're talking about a vertical spring. It's not that nothing would change. There is something that changes if you take a vertical spring to a different planet with a higher or lower gravitational acceleration. But the period and frequency wouldn't change. What would change is the maximum speed and the amplitude. Those could change. Those are the things that could change if you move a vertical spring to different planets. But it would still be, I'll give you kind of a sort of intuitive explanation. Actually, come to think of it, just in general, if you take the same spring and the same mass and the only thing you change is the amplitude. Notice amplitude has nothing to do with period or frequency. A lot of people get taken in by a common trick question where they tell you that the amplitude of the motion is changed and they ask what the period or frequency become, and the answer is nothing changes. So if, say, this is the equilibrium position, like the new equilibrium position after stretching against the weight of the block, and you pull it down even further to here versus the same spring and block, but now you pull them down this far and you let go and you let it move. What is the difference between these two? As far as period and frequency are concerned, nothing. As far as period and frequency are concerned, nothing. It's just that this one that got stretched further, it's going to have a higher maximum speed. So, yeah, it'll go farther, but because it also has a higher maximum speed, it has the speed and the increased amplitude just so happen to balance out in such a way that the amount of time it takes this block to return to here equals the amount of time it takes this block to return to here. This block And this block, actually, if you release both of them at the same time, if you yank them down this far and you release them both at the same time, they will reach the equilibrium position at the same time and then go up and then come back down to the equilibrium position, and they'll be next to each other at that time. Each time they pass the equilibrium position, they would be right next to each other. Only difference is that this one is going to have wider oscillations, but it also has the speed to compensate for that extra distance it has to travel. Yes, it has to travel farther, but it also has the extra kinetic energy needed to keep up with this one. So at the end of the day, same number of repetitions, same amount of time for those repetitions. And changing planets basically has a similar effect. It would just, I guess it would change where this new equilibrium line is if you move from a different planet, which is essentially just changing the amplitude. But period and frequency would remain unchanged. So don't fall for those trick questions. Mass does not affect pendulums, and acceleration due to gravity does not affect springs, not even vertical springs, as far as their period and frequency are concerned. And amplitude affects period and frequency for neither pendulums nor springs. Amplitude is only related to the maximum energy in the system. That's the only thing that would really be affected. The maximum energy, which therefore affects the maximum speed. But otherwise, amplitude does not affect period and frequency. So basically, amplitude matters for the stuff I covered last time. Whereas for the stuff I mostly focused on today, amplitude doesn't matter. That's the way you want to think about it. The way I've separated this chapter, I've separated like the time-related stuff into mostly this session and all the time-independent stuff into the previous session. Now then, there was another problem here that I wanted to do. Which one was it? This one just asks how many complete oscillations a certain pendulum makes in 5 minutes. We kind of did that earlier. You calculate the period, you take the 5 minutes, I guess you convert it to seconds, so what? 5 times 60 would be 300 seconds, and you take your 300 seconds divided by the period of oscillation. If, for example, the period was 2 seconds, 300 divided by 2 would be 150 cycles, 150 repetitions, or whatever it is. And I guess because it says how many complete oscillations, you would round it down to the nearest whole number. Even if it's like, 126.99, it doesn't matter. 0.99 is not a complete cycle, so you just cut it off. You don't round it up, you round it down regardless of what comes after the decimal point in this case, because it's worded how many complete oscillations it makes in 5 minutes. But yeah, we don't need to bother with that question. We already took a look at how to count oscillations in a given amount of time. This one, it's mentioning temperature because in this book, this actually comes after a chapter that talks about temperature extending the length of things. We're skipping that. It's talking about a pendulum that's made with like a wire for its string, and the wire, of course, is made of metal, and metal can stretch when heated. So if this was AP Physics 2, we would have learned how to calculate how much the metal would stretch per, degree of temperature change, and then you would calculate the new length of the pendulum and how the period is affected by that. But this is Physics 1, so we're not doing that. This one says a pendulum clock that works perfectly on Earth is taken to the moon. Does it run fast or slow there? Well, we already saw that the period on the moon is longer, so it would run slow because it would take more time per tick. How much more time? About, I guess, square root 6 times more time. And if you're wondering where I'm getting square root 6 from, the acceleration on the surface of the moon is about 1/6 of what it is on Earth. G for the moon is 1.67, and if you do 1.67 times 6, that's almost 9.8. 1.67 times 6. Okay, it's 10.02, but close enough. G moon is approximately 1/6 of G Earth. So then you would say period on the moon, period for a pendulum on the moon, assuming they have the same length, equals 2 pi square root L over G moon, period on Earth, equals 2 pi square root L over G Earth. And then if I were to just compare the two, T moon over T Earth, by the way, this is a type of question that you will see. Well, I mean, it's not guaranteed, but they like to ask these types of questions. How does the period change if the length is doubled, or if G is tripled, or whatever? We've seen questions like this before in the course. Things like, how does the momentum change if the kinetic energy of an object is doubled, or how does the force of gravity between two planets change if the distance between them is 1/3 of what it was before, or whatnot. We've done these sorts of questions before. These, I guess I'd call them factor questions. If one of your input variables changes by a factor of whatever, by what factor does your whatever you're calculating from that variable change? This is kind of the same thing. So the 2 pi's are going to cancel out. The L is the same in this case. So that's going to cancel out. And all that's left is the inverse square root ratio of the G's. So it's going to be equal to the square root of G Earth over G Moon. Hopefully that wasn't too far of an algebraic leap. I would hope that we've done enough algebra at this point that it doesn't bother you that I jumped straight from this to this. 1 over G Moon over 1 over G Earth is just G Earth over G Moon, and then of course keep the square root. So square root of about 6, right? G Earth over G Moon is a 6-to-1 ratio almost. So it's approximately square root 6, which is square root of 6 is about 2.449. I'll round it to 2.45. So period of the moon is about 2.45. Period of a pendulum on the moon is about 2.45 times what it would be on Earth, so it runs 2.45 times slower. That is the the clock mechanism that keeps track of ticks, it'll count less ticks, so the hands of the clock will move less often. So if you take two of these clocks and you leave one on Earth and you take the other one to the moon, the one that's on the moon is going to run behind. The one on Earth will say something like 3 o'clock, while the one on the moon is still saying 1 o'clock, because it hasn't ticked enough times to push the hands all the way to 3 o'clock yet. So yeah, it would run slow on the moon. Not because the amount of time that passed on the moon is different, but because the number of ticks that the clock actually counts is fewer. And then the second part of the question says, if the clock is started at 12 o'clock midnight, or 0 hours in military hours, what will it read after 1 Earth day, after 24 hours? And it says assume that the free fall acceleration on the moon is 1.63 meters per second squared, but we don't need that. We'll just use this 2.45 ratio. Okay, so on Earth, when 24 hours pass, when 24 hours worth of ticks pass, how many hours worth of ticks pass on the moon? Well, the moon runs 2.45 times slower, so this is another one of those questions where you just have to kind of common sense your way through it by just understanding your math. If it runs 2.45 times slower on the moon, then 24 hours worth of ticks on Earth divided by 2.45 tells you how many hours worth of ticks passed on the moon. 24 over 2.45 is 9.7959. Equals about 9.7959. So by the time the Earth clock has done 24 hours worth of ticks, the moon clock will still only be at the 9th hour, close to the 10th. 9.7959. I'm going to take that 0.7959, subtract 9 from my result, and multiply by 60 to get the minutes. So multiplying by 60 gets me 47.755 minutes, and then I'm going to subtract 47 from that number, keep all the other decimals, and multiply by 60 again to get seconds, and that's getting me 45.306. Okay, so the moon clock says 9 hours, 47 minutes, and 45.306 seconds since midnight, which means it says 9:47:45 a.m. Right? This is before the first 12 hours of the day. So the clock on the moon, if it has an AM versus PM display, it would still be saying 9:47 a.m. Any other ones here that are worth looking at? Well, that one ties into... Okay, so even if I hadn't forgotten, this problem would have reminded me anyway. That thing that I wrote down on my notes a little bit ago, it's finally here. So this, I would hope they're not going to ask you at all, but you might be asked to do this, and you can probably just kind of use your intuition to figure it out. It's a bit much, I would say, for Physics 1, but it's not impossible. It's more difficult to justify than it is to actually do. I think a lot of students would be able to figure this out without thoroughly proving anything. But it says, a simple pendulum is 5 meters long. And it's asking, what is the period of simple harmonic motion for this pendulum if it is located in an elevator accelerating upward at 5 meters per second squared? And then it asks if it's in an elevator accelerating down at 5 meters per second squared. So a pendulum, a simple pendulum, in an elevator. It's a simple pendulum, but the twist is that it's in an elevator. And the elevator can accelerate up or down. So they were asking for frequency or period again? They were asking for period. Okay, and they told us the length was 5 meters, was that right? Yeah, length is 5 meters. Length is 5 meters. So what is the period if it's accelerating up versus down? So period, of course, is 2 pi square root L over G for the simple pendulum. Except when it's in an elevator accelerating upward, from the pendulum's perspective, it feels like G is greater or less than 9.8 when you have some external acceleration on top of it. So when the elevator is accelerating upward, from the perspective of this mass that's attached to the string in the pendulum, from its perspective, it's basically similar to being in a non-accelerating elevator with a greater G. So the acceleration, they said, was 5 meters per second squared in magnitude. When accelerating upward, that's the same as not accelerating at all while experiencing a gravitational acceleration that is 5 meters per second squared more than 9.8. And when you're accelerating downward, it's the opposite. It's when you're holding something by a string. Let me see if I can grab something real quick that I can use as an example. Well, I guess this yo-yo over here will work nicely for us. Let me just unwind the whole string first. So when I let this thing down, if I accelerate my hand downward, if you imagine you were in the position of the yo-yo, if you imagine you were the one that was tied here, and then somebody just kind of started letting you down faster, then you would feel as if you weighed less, right? You would feel as if you weighed less. You would feel as if there was less acceleration due to gravity, versus if they actually tried to yank you up, you would feel heavier. So that's kind of the intuitive explanation. As for the mathematical explanation, it's a bit more difficult, but I can try and give you something somewhat convincing here. It's been a while since I've done this, so I have a feeling I might screw it up, but let's go ahead and try figuring this out anyway. Let's try and figure out what the perceived acceleration of the pendulum is. So with a pendulum, of course, you're going to have some sort of tension force and some sort of gravitational force. And you're going to have, this time I'm actually going to break the tension into components. And you're going to have an acceleration in y, mass times acceleration in y is equal to force of tension y minus mg, whatever that amounts to. And for the acceleration in x, you would just have force of tension x, and that's it. Okay, so the x part doesn't really matter to us. It's the y part that's going to matter. So if you're working with an acceleration in y that is, let me see. Let me try and remember how I did this before. It's been a while since I've actually done this. So essentially what you would do is you would add mg over to the left hand side. So mg is equal to force of tension y minus m times acceleration in y. And then if you divide by m, then g is force of tension in y over m minus acceleration in y. And this acceleration in y would have to be, the acceleration in y of the pendulum would have to be its own acceleration plus any external acceleration. Acceleration in y would have to be the acceleration from the pendulum's frame of reference, just the acceleration that the pendulum would have normally when it's in an elevator at rest or hanging from a ceiling at rest, plus whatever external acceleration it's experiencing. That would be the total acceleration of the pendulum at any given moment while it's swinging around. So when the external acceleration is 0, of course, g is just its normal value. But when this external acceleration is not 0, then when it's accelerating up at 5 meters per second squared, you're basically adding 5 meters per second squared to this. So it would be g equals, on the way up, I'll call it g up, is equal to force tension y over m minus a pendulum plus a external. Whereas when, plus a external, and then if the acceleration is upward, then that's just positive. You're just, no, wait, but that's the term that's being subtracted. You see, this is why I wish I had remembered to think about this before starting the stream, because I made a mistake somewhere here. I can feel it. I've done something wrong here. But there should be a way. I think I've just set up my math incorrectly. Well, we can just save it for next time. But for now, you're just going to have to take my word for it. And I think most people's intuition would agree that when the elevator accelerates up, the effective acceleration due to gravity is as if it was 5 more, and when the elevator is accelerating down, it's as if it's 5 less. I wouldn't worry too much about this showing up on the AP exam, but if it does, I don't think too many people will be caught off guard by it. I think most people will be able to figure out that they need to do this. So yeah, on its way accelerating up, it's just 2 pi square root L over G plus 5, so that's on the way up. And on the way down, period will just be 2 pi square root L over G minus 5. And you can plug in those numbers and get the actual values of those periods if you really want to. But I am just going to leave it there. And yeah, next time I need to remember to do this more properly. I feel like I might almost have it right now, but I'm forgetting something. I'm missing something here. So we'll just save it for later. Now then, I think that is enough pendulum questions. Do we have one more? No, we don't really need to do that one. Yeah, I think it's time to talk about the physical pendulum. And let's see, so physical pendulum I can check off, I did that. I'm gonna need to revisit that. We talked about those factor questions. Right, and we've got, okay, that after physical pendulum. So physical pendulum is basically the last thing that we need to talk about for this chapter. And then that little thing from rotational dynamics that I forgot 2 streams ago, and then we'll be done for the day. So, the physical pendulum. The physical pendulum. I mentioned what a physical pendulum was last time, but we held off on trying to come up with any equations for it. How are the period and frequency of a physical pendulum calculated? Well, the way we derived period and frequency for the mass spring system and the simple pendulum last time was we took, where was it? No, it wasn't this. Actually, yeah, we found the angular frequency. We determined that the angular frequency for a spring was the square root of the coefficient of the restoring force divided by mass. And similarly for the pendulum case, angular frequency for a pendulum, we did the same thing, square root of the restoring force constant divided by the mass. So that's what we're going to do again for the case of a physical pendulum. Where did I actually... I could have sworn I wrote a more general version of the formula, but anyway, omega is equal to the square root of beta over m. Beta is just what I'm calling it, but if somebody out there knows a more official variable for it, I don't. So if a restoring force has a formula of the form negative constant times displacement like this, then the angular frequency for an object moving subject to this restoring force will be equal to the square root of that constant divided by the mass. And there's always going to be a mass, because in order for something to be in simple harmonic motion, it has to physically be a thing that has mass to it. Okay, so we need to figure out what this constant is for a physical pendulum, for some randomly shaped object that swings back and forth. So this is going to be like the pivot point that it is hung from, that it swings around. And then I'm going to pick another point that will be the object's center of mass. I'm going to pick another point on the object and call that the object's center of mass. So that will be the center of mass. And so this object will, of course, swing back and forth. If hung in this way, it'll swing back and forth. Just like a simple pendulum, it'll go back and forth like this. Okay, I guess I drew that arc a little. Okay, that's a little bit more symmetric. And I need to figure out what the restoring force formula is in the case of a pendulum. Well, you might guess that moment of inertia is going to factor into this. You might be able to guess that right away because essentially, if you wanted to break this down into a bunch of little pieces, you could treat each piece as a simple pendulum, and then with some calculus, you could come up with some sort of formula, just treating this as an infinite number of simple pendulums. Or we could just use the moment of inertia in some way, because that already has the calculus kind of done for us. So that's what I'm going to do. What I want to do is start off with the angular acceleration, actually. So the restoring force, whatever it is, it's equal to the mass times the restoring acceleration. So I want to find this acceleration, and to find this acceleration, let's find the angular acceleration first. To get the angular acceleration, I would just take the, I would take the radius of, I guess I would call it the radius of curvature times the angular acceleration of the object at any given point in time. Unfortunately, the angular acceleration is not constant, so we can't just use rotational kinematics and stuff. We can't just manipulate what we already had for the simple pendulum, but we have a way around this. We can do net torque equals I times alpha. And the torque on this object, the net torque on it, would have to be just due to the acceleration from, or not the acceleration, the force of gravity. The force of gravity, of course, acts on the object's center of mass, which is why I highlighted it. Force of gravity acts on the object's center of mass. There is going to be, of course, a normal force from the hinge so that the net force on it is 0, but the net torque will not be 0. So there is going to be some sort of normal force over here, and I'm assuming this is a smooth axle, so there's no friction causing torque. So the only torque on this object is due to the force of gravity. It's going to depend on this distance over here, which in most textbooks is called either lowercase l or capital L. I'll call it capital L. It's the distance from the pivot point to the center of mass. Be very careful about that. L is pivot to center of mass. So if your physical pendulum is, say, a meter stick, don't use the length of the stick. Just because this is called L doesn't mean it's a length. Pivot to center of mass distance. And I know some textbooks call it different things because L does create that potential for confusion. But I can also see why they used a capital L in my textbook because, you know, a physical pendulum is still a pendulum of sorts. So I guess they wanted to relate it to the simple pendulum by still using an L here, even if it's not the same kind of L. Anyway, this L is pivot to center of mass distance. We can use this as our pivotal displacement, as I called it a few episodes ago. And we can say then that the net torque is just the torque due to gravity is equal to the force of gravity times the pivotal displacement times the sine of the angle between their directions. And the angle between their directions would be, I should have drawn this bigger, but I'll just draw a copy of it over here. So there's your pivot point, there's your center of mass, there's your mg, there's your pivotal displacement from the pivot to the point where the force is being applied, and then if theta is the angle made with the vertical by the physical pendulum, then theta is also the angle between the directions of this pivotal displacement and mg. So we can just use that as our theta. Well, we said last episode that this theta is subject to the small angle approximation. Right, we used the small angle approximation. As long as you don't pull this physical pendulum too far, and again, the definition of too far depends on opinion to some extent. Some people say 30 degrees is fine, other people say anything farther than 15 degrees is too far, but whatever you agree on to be a reasonable limit for theta, within that limit, sine of theta will approximately be equal to theta. This, of course, needs to be in radians. I don't know if I did mention that last time, but needs to be in radians for this to work. And you can kind of see, I don't think I did this last time, but we could do a sample calculation. If theta is 30 degrees in radians, 30 degrees is pi over 6. And then if we do sine of 30 degrees, well, sine of 30 degrees, sine of pi over 6 is 1/2. And we can kind of see it. Sine of pi over 6 is 1/2 is equal to 3.14 over 6. That's almost 3 over 6. That's almost a half. So yeah, this is pretty legit. 3.14 over 6 is 0.5233. Approximately. 0.5 is approximately 0.52 with a bunch of repeating threes. I guess this might be enough of a margin of error that some people won't tolerate it. But yeah, somewhere below 30 degrees is where you want to be for this to work, for this approximation to hold. So L times mg times sine of theta, which really is just L times mg times theta for small angles, is equal to I times alpha. Okay, that allows me to get my angular acceleration. So if I just divide by the moment of inertia now, then I get angular acceleration is I'm going to write this as mgl theta over I. And then I'm going to multiply by, well, what is my r here? What is my r? If I'm just following the movement of the center of mass, then my restoring acceleration is going to be the component of my restoring force, which is a component of the force of gravity that's acting on the center of mass. My restoring force is still some component of gravity that's acting along this tangential direction over here. And it's acting at this position. So the acceleration should be of this position over here. So the r that I need to use is also this capital L. So if I just divide by r, which is capital L over here, then alpha is equal to the tangential acceleration over L. mg L theta over I equals A over L. Multiply the L over to the left-hand side, and you get A equals mg L squared theta over I. But we're not done yet, but because theta can also be written in terms of, I guess, arc length and L, or I guess we could also call it x. Yeah, I'll do that. I'll call it x over L. Theta, in a similar fashion, is equal to x over L. Just using the arc length equals r times theta relationship over here. Using x for my r, or no, using x for my s rather, and L for my r. S over r, or x over L is what we'll call it over here. So if I replace theta with x over L, then I've got mg L squared times x over L all over I. One of the L's cancels out. That will be the restoring acceleration, mglx over I. Okay, let's take this now and put it in here and see what our beta is going to be then. If I put this in here, then I get m times mglx over I equals negative beta x. The x's cancel out, and beta is going to be the absolute value is going to be, beta is going to be equal to, x's get canceled out, is going to be m squared gl over I. Okay, let's plug this in here now. So we get the angular frequency for a physical pendulum is m squared gl over m. The m's cancel out. Oh, m squared gl, I forgot the I. M squared gl over I, and then that over m, so I times m, is going to be our angular frequency. So angular frequency is equal to the square root of mgl over I. Well, let's try and see if this still works for the simple pendulum. That would be a great way to check and make sure that this actually works. So this is omega for a physical pendulum, omega physical. Let's take a look at if this was a simple pendulum. If this was a simple pendulum, well, then it would basically be using the length of this string as our big L, right? The center of mass of this object is just going to be at L distance away from the pivot. And the moment of inertia of this thing would be a point mass. So for the simple pendulum, I of the simple pendulum is going to be just moment of inertia for a point mass. That's mr squared. Here our r equals L, so ml squared. Okay, if I try and plug this in for I of the simple pendulum, then omega of the simple pendulum using the physical pendulum version of the equation would be square root of mgl over ml squared. The m's cancel, one of the l's cancels. Oh, would you look at that? Square root g over L, and this big L is actually equivalent to the little l that we use for the length of the string in the simple pendulum. So, let's see, where was it? I think it's over here. Yeah. For the simple pendulum, square root g over L. It's the same result, so that tells us that we must have done something right. That gives us some faith that this is a valid equation that we have over here. So omega for the physical pendulum is the square root of mgl over I. And that's really all we need to do. I guess we can write the period and frequency equations from this, but otherwise we're done with the chapter. You probably won't get asked a lot about physical pendulums. Maybe there will be like one throwaway question. Maybe it'll be like a free response question where they introduce this equation to you, because I don't think this one is on the formula sheet for the AP exam. I'm pretty sure it's not. It's just that uncommon. But even if they do give you one, really the only big thing here that is a potential for mistakes is people getting confused about the definition of L. It's the distance from where the pendulum is hung, where the hinge pivot is, to where the center of mass is. As long as you get that right, you'll be fine. I could see people falling for, like, if they give you a pendulum that is like a rod or a meter stick, and people use the full length of the stick for L instead of using half of its length. I could see people getting caught by that. And I guess the other big potential for mistakes is using the correct moment of inertia. You would have to use your hinge over here, your pivot, as the axis of rotation for calculating moment of inertia. So some people might end up using, again, if it was a rod, we know two formulas for the moment of inertia for a rod, one through its end and one through its center. Make sure to use the moment of inertia for a rod rotated through its end, because that is where it's being rotated through. But yeah, apart from that, I don't think it's that much harder. So anyway, omega of the physical pendulum, is equal to square root mgl over I, and since omega is equal to 2 pi times the frequency, then that tells us that frequency is omega over 2 pi, and 1 over the frequency is the period, so the period must be 2 pi over omega. So I'm going to write the period equation, and you can use its reciprocal anytime you need frequency. Period for a physical pendulum, period for a physical pendulum is 2 pi over omega, 2 pi times 1 over this. So 2 pi times the square root of I over mgl. And if you ever get confused about which one's in the numerator and which one's in the denominator, you can just do this. You can just, if you've memorized what it is for the simple pendulum, then all you would have to do is substitute ml squared over here and see if it simplifies to square root L over G for the simple pendulum. Just plug in ml squared for your I and see whether or not you get the correct form by comparing it to the equation for the simple pendulum, and you will be fine. Let's see if we can do like 1 or 2 questions with this, and then that won't be it, because there's one more thing I need to cover. I'm so glad I wrote down my notes, because I was about to forget it again. There's one thing I forgot to do for angular momentum. Let me see, I think I found one earlier in this other book. Where was it? Maybe it was on this page. Ah, here we go. So it says a physical pendulum consists of a meter stick that is pivoted at a small hole drilled through the stick, a distance x from the 50 centimeter mark. The period of oscillation is observed to be 2.5 seconds. Find the distance x. That is what they're asking for. A physical pendulum consists of a meter stick that is pivoted at a small hole drilled through the stick, a distance x from the 50 centimeter mark. That's distance from the center. Oh, well, we know that. Or at least, oh, okay, I see what the twist is. Okay. This might actually be a little bit more time consuming than I thought. But we have a way to deal with this. So it says physical pendulum with a meter stick. The hole is drilled some distance x from the center of the meter stick. So that's going to be our big L, basically. That's going to be our L over here. We've got a hole drilled somewhere in here. We don't know where exactly, but that's going to be our L. They called it X, but for us, I'm just going to reword the problem, solve for L. And actually, it's a lot more time consuming than what I would have assumed when I first encountered it earlier today. I didn't read the whole thing. I just saw a physical pendulum consists of a meter stick and thought, good, we'll do that one. I guess the lesson here is read the full problem before you present it live to a random audience before you end up making a fool of yourself. Okay, the period of oscillation is observed to be 2.5 seconds, so t is equal to 2.5 seconds. Find the distance x. Okay, well, let's solve for what we can solve for right now. Oh, wait, actually. Okay, let's write equations and you'll see what the problem is. So t equals 2 pi square root, and this is going to be I over mgl. I over mgl. And we know g, we don't know m. Not that it's going to matter because it's going to cancel out. And we need to solve for L. So here's the problem. We need to find I. Normally this would be a calculus problem, but I showed you a method for finding moment of inertia of a rod-shaped object through any axis by simply splitting it into two rods. So we have a rod of this length, whatever it is. I guess this would be 0.5 meters minus L would be the length of the segment that's above the hole. And then the rest of it would be, well, this is going to be half of a meter, so 0.5 plus L would be this part. And then if we add 0.5 plus L to 0.5 minus L, we get 0.5 plus 0.5, and the L's cancel out, which would be a total of 1 meter, which is the full length of a meter stick. So yeah, our math is correct so far. All right, moment of inertia for a rod. Moment of inertia for a rod was through its end. Moment of inertia for a rod-like object through its end is equal to 1/3 of its total mass times its total length squared. I'm going to call it big R squared here because I don't want to call it big L for obvious reasons. Big L has a different meaning here. So I'm just going to use R. Okay, 1/3 big M big R squared. Well, if I treat this as two rods rotated through their ends, then I of this particular meter stick is going to be 1/3 mass of the little piece times R of the small piece squared, ms, rs, s for small, squared, plus 1/3 mass of the large piece plus, or rather times, R of the large piece squared. And the mass of the small piece and mass of the little piece can be defined in terms of the total mass. So the mass of the small piece is going to be proportional to its length. It's going to be 0.5 minus L over the full length, which is 1. 0.5 minus L over 1, that's the fraction of the length that the small piece takes, and multiply that by the total mass, and there you go, that's the fraction of the mass that the small mass would be. And then the larger mass would just be the remainder of that. You could do 1 minus m small. Wait, could we? No, you would do big M minus m small is what I mean to say. So m large, you could do it that way, or you can just do 0.5 plus L over 1. 0.5 plus L over the full length 1 times the total mass. Okay, I think we're going to need a new sheet. Yep. This turned out to be a bigger time commitment than I thought it would be. What have I done? And here I thought I would already be preparing food at this hour. Okay, switch pens first off. And then I guess the big M is actually, I called it little m here. You know what? I'll change this to big M. Yeah, that'll keep everything consistent. Okay, so period equals 2 pi square root, moment of inertia is going to be, there's a 1/3 in each piece, so 1/3 of 0.5 minus L times big M plus 0.5 plus big L times M. Yes? Oh, one more parenthesis there to close it out. Actually, I'll turn them into square brackets so that it's more readable. Yeah, that's easier to see. Square brackets are better here. Wait. No. I forgot this. I forgot the squares. Okay. So 1/3. Okay, rewrite it. I messed it up. T equals 2 pi square root. Okay. 1/3 times 0.5 minus L times big M times the length of that piece, that's the small piece, so times its length squared times 0.5 minus L squared plus 1/3, do the same thing for the large piece, 0.5 plus L over 1 times the total mass of the meter stick times its length squared, 0.5 plus L squared, all over mgl. There we go. This is going to be quite the mess. But we can work with this. 2 pi square root. I will factor out the 1/3 and the m, and that will cancel out with the m down here, leaving us with, I feel like it's going to be a quadratic in the end. Let's see, 0.5 minus L all cubed, 0.5 minus L all cubed, plus 0.5 plus L all cubed. Yeah, this is definitely beyond anything they would ask you on the AP exam. But I guess the good news here is if you can do this, you can do anything they throw at you, hopefully. Okay, equals 2 pi square root 1/3. Okay, to FOIL a cubic, it's 1331. So it's 0.5 cubed plus 3 times 0.5 squared. Wait a minute. No. It's minus 3 times 0.5 squared times L. Plus 0.5 L squared, and then minus L cubed. That's foiling this first one. And then plus, this will be another 0.5 cubed here. At least it's all pluses, so that's the saving grace. Plus, oh, and I forgot a 3 there. I forgot a 3. That was a close call. 1331. Yep. 0.5 cubed plus 3 0.5 squared L plus 3.5 L squared, and then plus L cubed, plus L cubed, plus L cubed, and then close those parentheses, and then just close the square brackets. And then all that over GL. Sorry that it's starting to look a little ugly. Let's extend that square root a little bit. Okay, 0.5 cubed plus 0.5 cubed, that's not canceling out. Minus 3 times 0.5 squared and plus 3 times 0.5 squared. That is going to cancel out. This cancels out with this. 3 times 0.5 squared L, you are gone. Also, minus L cubed cancels with plus L cubed. So we are left with 2 pi square root 1/3. 0.5 cubed plus 0.5 cubed is 2 times 0.5 cubed. That's the same as, well, 2 cancels with one of the 0.5s, and that leaves me with a 0.5 squared, which is 0.25. And then we've got 3.5 L squared and another 3.5 L squared. That's 6 times 0.5 L squared, or actually, wait, no, 3.5 L squared times 2, and then the 0.5 cancels, and we're left with 3L squared. Yeah, plus 3L squared. And then that over GL. Okay, they told us the period was how much again? It was 2.5 seconds. So now we divide by the 2 pi and square both sides. So 2.5 over 2 pi squared is equal to 1/3 of 0.25 plus 3L squared over GL. Here's hoping I didn't make any mistakes along the way. Multiply by GL Oh yeah, it's definitely a quadratic. Multiply by GL and also multiply by 3 to cancel the 1/3. So it'll be 3 GL. I guess we'll substitute in the value of G. So yeah, 3 GL times this stuff. And then what I would want to do is subtract it over to the right-hand side. So let's continue up here. 3 GL times 2.5 over 2 pi squared equals 0.25 plus 3L squared. And then I'm going to subtract all this over to the right and get 0 equals, I'm going to write the 3L squared first, and then minus, that'll be 3G times 2.5 over 2 pi squared, and then L, and plus the 0.25. Okay, quadratic formula time. L equals negative b plus or minus the square root of 4ac all over 2a. So negative this stuff, we'll cancel that negative and you'll just have 3g 2.5 over 2 pi squared plus or minus the square root of this stuff squared, I'm just going to call it b squared, minus 4 times 3 times 0.25, and then all over 2a, all over 2 times 3. Okay, the 4 and the 0.25 simplify to a 1, so yeah, let's figure out what this b is. I don't see anything that can simplify in here. So it's time to plug in the numbers and see what we get. 3 times 9.8 times, parentheses, 2.5 over 2 pi, close parentheses and square, and that is about 4.65444. I'll do 4.654 for now. So 4.654 and 4.654 squared is needed in there. So 4.654 plus or minus the square root of, if I simply square this, that's about 21.664. 21.664 minus 3. Well, at least the good news is the stuff under the radical is positive. That's a good sign. All over 6. Okay. So I'm going to do 4.654 plus square root of 21.664 minus 3 all over 6. And that gives me, in the positive case, I get 1.496. In the negative case, if I just copy over my equation and switch the plus to a minus on my calculator, in the minus case, if I do minus the square root, I get 0.055, and which, well, 0.0556, so I guess it would round to 0.056. Okay, which of these can we throw out, and why? It's been a while since we've done one of these. We can throw out this one. Because L equals 1.496 meters is implying that the meter stick is being swung from a point outside of the stick. A meter stick is only 1 meter long. There's no place to drill a hole through it at 1.496 meters away. So L must be 0.056. L is equal to 0.056 meters. In other words, the hole is drilled at the 55.6 centimeter mark. At the 55.6 centimeter mark on the meter stick. Alright, I never want to do a problem like that ever again, even though I probably will. Now, one last thing before I wrap up, which is something I forgot to do when discussing angular momentum 2 streams ago. Just a quick conceptual thing. I said I was going to do this in the stream and I somehow forgot to do it. One of the things that we mentioned during that stream is that an object moving in a straight line does have an angular momentum, and I said that there's a way that we know this is true based on how collisions work. So here is the idea. It's a very simple conceptual idea. An object moving in a straight line must have some sort of angular momentum, because how else do you explain this? Here we are looking from above at a frictionless table. So these two objects are on a table. You know, you've got a ball and a stick, and the ball collides with the stick, but the table is frictionless, so when it collides with the stick actually moves, and when it moves, it rotates. When it moves, it rotates. That implies then that it gained angular momentum in the collision, but where did it gain it from? Well, it has to have taken some angular momentum from this object, because initially it wasn't moving. So that's just a quick conceptual scenario that allows you to understand that an object moving in straight lines does indeed have an angular momentum. So that's one. 2, if you were to slide something across a table to hit a stick, the axis of rotation, of course, would be the center of mass. If this thing is not pinned down, if it's not nailed down anywhere, then the axis of rotation would just be the center of mass. When an object is free to rotate, it will naturally try to rotate about its center of mass. So if you pick and choose where on the stick you want the collision to happen, you can actually influence how much angular momentum the stick gains versus linear momentum, because in this type of collision, both types of momentum would be conserved. This object is going to have a linear momentum after the collision. So after the collision, the initially sliding object, maybe it continues just moving slower, or maybe it bounces back and goes to the left, whatever the case may be. And the stick, along with the angular momentum that it gains, along with this rotational motion, it's also going to have translational motion due to the conservation of linear momentum. So where the collision happens matters. If we want full translational motion only for the stick, where would the collision need to take place? If you guessed at the center, you guessed right. If you get a problem like this, then the only way for a collision to occur between these objects without any transfer of angular momentum is for the moving object to hit this other big rigid object and hit it right over here on its center of mass. That's the only way that you would get a collision where the result is this stick just moving translationally without any rotation. Because if you use this as the pivot point, what is the angular momentum of this colliding object about this point? Well, it would be 0. We said that angular momentum of an object moving in a straight line is r cross p. We said angular momentum for an object that is moving in a straight line, an object that has linear momentum, is r cross p, where r is the displacement between the point about which the angular momentum is being calculated and the center of mass of the object that has that linear momentum. So r is basically, let me grab orange. R is basically this. So you do, it's equal to r times p times sine of theta. Over here in this collision, r is actually this over here, and then r times sine of theta would be this distance over here, which is the more important thing. This over here would be r sine theta, and then you take that r sine theta times the linear momentum mv to calculate how much angular momentum this thing has. You don't get to choose this pivot point for calculating the angular momentum. You don't get to choose it in this collision. It's already chosen for you. If the stick is nailed down at some point, if it's being held down, like say I have this and I have something sticking it to the table so that when you collide with it, it has no choice but to spin about that fixed axis, then that is the pivot point that you would use to calculate the angular momentum of the colliding ball. And if it's just a stick that's free to rotate, then you would have to use the center of mass. And yeah, if you collide directly with the center of mass, well then r is going to be in this direction, shrinking slowly. Once you hit it, r is actually going to be 0, but even when it's not, the angle between the direction of r and the direction of this object's momentum is 0 or 180 degrees, depending on how you want to look at it. Either way, sine of 0, sine of 180 degrees, it's 0. So you would have no angular momentum along this line of collision. There would be no angular momentum to transfer, so what would happen is the ball would collide with the stick and the stick would just move without any wobble, without any rotation. You can actually try this with a ruler. I know the hole in the ruler kind of throws a wrench in things, but you can try hitting it somewhere around the halfway mark, the 6-inch mark, and see that it barely tilts, versus if you hit it anywhere else, it rotates for a bit until, of course, air resistance and friction stop it. That is now the last thing that I needed to cover for today. So, next time, whatever next time may be, I actually might need to do a little bit of prep because I don't get a lot of requests for Physics 2, so it's been a while since I've last taught any fluid mechanics. But next time, for you Physics 1 students, it'll be fluid mechanics. I'm guessing it will take 2 or 3 streams to finish up that chapter, but we'll see. I'm going to make some notes for myself and just kind of plan out how I want to cover it, since it's been a while since I've done that. And 2 to 3 streams is my estimate. So for the Physics C students, take this time to review, and once I'm done covering fluid mechanics for the Physics 1 students, then I will go ahead and start reviewing everything that we've done up to this point, just with the calculus being added in. I will probably cover multiple chapters worth of topics per stream once we get there, because if I go chapter by chapter, those are going to be really short streams. Some chapters have a lot of calculus in them, some not so much. So yeah, expect a sort of mixed review of sorts where I throw calculus into the mix. And yeah, so give it 2 or 3 streams before coming back if you're Physics C. If you're Physics 1, you're going to want to stay tuned, and then you guys get to tune me out for pretty much until the AP exams come, unless I make the time to do like a review stream. We'll see. I haven't yet fully established my schedule for the lead up to the AP exams, and I'm not entirely sure if it would even be worthwhile for me to do a review stream, considering that I already have some old ones, and there are already other people who've made videos in the past that cover, like, you know, past AP problems, and I'm not entirely sure what I would want to cover if I were to do something like that. I mean, it would be nice if I could just sit there and wait for people to come in and ask questions, but that probably isn't going to work out very well right now. There has been some activity in chat occasionally here and there, but not enough that it could provide enough questions for an entire stream. So I would have to actually have some problems ready to go, or just something to cover. And I'm not sure what to pick, given the stuff that I've already done in previous reviews. So still kind of up in the air as far as review is concerned. I'm not sure either way whether I'm gonna do that or not, but at the very least, I do want to see the course through. So we will get that done. Let me think. Anything else as far as announcements are concerned, or anything like that? For homework, of course, you're gonna want to look at the other stuff that I posted on the course plan. If you're new here, the course plan is linked in the description. If you scroll down to the simple harmonic motion section and click it, it'll open up, and here I can just show it on screen. So if you click the link in the description, you'll be taken over here. Go down to simple harmonic motion and scroll down to, you should have already done the simple harmonic motion worksheet from last time. Take a look at the spring problems and the pendulum problems, which I believe I have a video for one of these or both, if I'm not mistaken. I think it was from last year. I'm trying to remember. What did I do last year? It was one of these problem sets. Maybe it was a worksheet that I didn't even post over here. And of course, if you want to look at the problems and exercises in the OpenStax book, which is linked over here at the top, if you want to download it, it's a free book. you can just go here, skip to what chapter was it again? It was chapter 16 in the book. So yeah, go to the table of contents, skip over to chapter 16 here, and skip to the problems and exercises and pick a few from here if you don't have your own textbook. If you do have your own textbook, then you might find better problems there. And of course, look at the worked examples. This guy has a playlist where he does a lot of example problems that I think might be worth looking at. And I think that is it. So next time, if you want to prepare for fluid mechanics, for those of you in Physics 1, then you can do the reading in chapters 11 and 12 from that same book, from this OpenStax book. And yeah, I think that is it. So I will go ahead and start making notes for what I want to cover in fluid mechanics. And I will post a stream on the schedule at some point. It's probably going to be Sunday. But then again, I have been kind of rescheduling all my streams lately. They haven't been occurring on Sundays for the past, I don't even know how many weeks, and I've been kind of shuffling around the schedule because of real life stuff going on. But whenever next time is, we will do fluid mechanics. Until then, take care. Hope you learned something good today. And I forgot what I was going to wrap up with. Take care. Hope you learned well. Class dismissed. I will see you next time.